At some point, if you look far enough into space, you stop seeing stars and start seeing time. Every photon from a distant galaxy carries a message from the past, a snapshot of what the universe looked like billions of years ago. But there's a boundary we can't cross, no matter how powerful our telescopes become. Not because of technology, but because of physics. Beyond that edge, light hasn't had enough time to reach us. It's a cosmic horizon, and it limits what we can know. But what if we could reach further? What if we could build telescopes so advanced, or discover methods so strange, that we could peer beyond that boundary? What has NASA already seen near that edge? This is a journey through the limits of observation, and what might lie just beyond. When telescopes first opened the heavens, in the early 1600s, nobody had ever truly seen space. People looked at the night sky with their eyes alone, and for thousands of years that was enough. The stars were tiny lights. The moon was a glowing disk. The planets moved in mysterious ways, but their details were invisible. Then came a simple device, two pieces of glass in a tube, that changed everything. The telescope didn't start out as a tool for astronomy. The first known versions were built in the Netherlands around 1608. They were used mostly by merchants and soldiers. The device made faraway ships look closer. It was a clever trick of lenses, useful for spotting danger or tracking goods at sea. But when news of this invention spread across Europe, it caught the attention of someone who saw a different use for it. Galileo Galilei. Galileo didn't invent the telescope, but he made it better. He ground his own lenses and built more powerful versions than the ones available before. Then, in 1609, he turned it toward the sky. That moment marked the beginning of a new age, not just for astronomy, but for how we think about the universe. The heavens, which once seemed still and perfect, were about to become full of movement and detail. The universe, which had seemed calm and ordered, was about to surprise everyone. One of Galileo's first targets was the moon. People thought it was a smooth, polished sphere, like a crystal. But through the telescope, Galileo saw something very different. He saw mountains, valleys, and craters. Shadows moved across ridges as sunlight hit them at different angles. The moon was not perfect. It was rugged and broken, just like Earth. Next, he looked at Jupiter. What he found was even more shocking. Orbiting around the giant planet were 4 tiny points of light. Night after night, they moved. Sometimes they disappeared behind the planet, then reappeared. These were not stars, they were moons, tiny worlds revolving around something other than Earth. This was the first time anyone had seen clear evidence that not everything revolves around us. The Earth wasn't the center of everything. Galileo's discovery challenged centuries of belief. He also turned his telescope to the Milky Way. To the naked eye, it looks like a pale smear of light across the sky. Through the telescope, it exploded into thousands of stars. What seemed like a single band was actually made of countless points of light. The universe was not sparse. It was packed with stars, stretching far beyond what anyone had imagined. Each of these discoveries chipped away at the old ideas. For centuries, people believed the heavens were fixed and perfect. The planets were supposed to move in perfect circles. The stars were thought to be placed on a crystal sphere. Everything beyond Earth was part of a divine, unchanging order. But now the telescope was showing craters, motion, moons, and mysteries. The sky was not calm, it was full of action. These early telescopes were primitive by today's standards. They had narrow fields of view and blurred edges. Still, they gave people a glimpse of a reality they had never known. And just as important as what the telescope revealed was what it made possible. Better tools let us see more, and the more we saw, the more questions we had. This pattern, tool, discovery, deeper mystery, has repeated again and again. The first telescopes showed that the moon had terrain and that planets had moons, so better telescopes were built. With those, astronomers found more moons, rings, faint stars, comets, and strange objects that didn't follow any known pattern. They found Neptune by watching the way Uranus wobbled. They discovered galaxies beyond our own by seeing faint smudges of light that turned out to be whole island universes. The telescope opened the sky, but also showed how much more there was to find. Galileo wasn't alone for long. Others quickly joined the effort. Johannes Kepler improved the design of telescopes and used them to better understand planetary motion. Later, Isaac Newton created a new type of telescope using mirrors instead of lenses. This allowed for clearer images without the rainbow-like distortions that early lenses sometimes created. Each step forward revealed more of the universe and more of its strange behavior. Why deep space is a time machine. When we look up at the night sky, it feels like we're seeing the stars as they are right now. But that's not quite true. What we're really seeing is what they looked like some time ago. That's because light doesn't move instantly. It travels at a fixed speed. A very fast speed, yes, but not infinite. Light from the moon takes about 1.3 seconds to reach Earth. Light from the sun takes a little over 8 minutes. So when you look at the sun, though hopefully not directly, you're seeing it as it was 8 minutes ago. The deeper you look into space, the older the light becomes. This simple fact has huge consequences. When we look at a star that's 100 light-years away, we're seeing it as it was 100 years ago. When we look at a galaxy 1 million light-years away, we're seeing it as it was 1 million years ago. The further away something is, the further back in time we are looking. In this way, space becomes a kind of time machine. In everyday life, this delay is so small that we don't notice it. Even the signals we send to the Moon or Mars, though slightly delayed, are still close enough that we can interact in nearly real time. But space is huge. Once you get beyond our solar system, the distances stretch so far that even light, traveling at nearly 300,000 kilometers per second, takes years, thousands of years, even billions of years to get here. Telescopes, especially the large ones placed on mountaintops or in space, collect light from objects that are unimaginably far away. Some of that light has been traveling through space for billions of years. One of the clearest examples of this came with the Hubble Space Telescope. In the mid-1990s, scientists pointed Hubble at a dark patch of sky. This spot was no bigger than a grain of sand held at arm's length, and from Earth it looked completely empty. No bright stars, no obvious galaxies, just blackness. They kept the telescope focused on that spot for days. As the long exposure built up, the image began to change. Hundreds of tiny shapes emerged, galaxies, each filled with billions of stars. Some of them were faint and red, barely visible. Those reddish colors were clues. Because the universe is expanding, the light from distant galaxies is stretched out as it travels. This makes it appear redder than when it first left the galaxy. The more distant the galaxy, the more its light has been stretched, what scientists call redshift. By measuring this redshift, astronomers could tell how far away those galaxies were and how far back in time we were seeing. Some of the galaxies in that photo were from when the universe was less than 1 billion years old. They had been sending their light toward us for over 12 billion years. We were seeing young galaxies, baby galaxies, from the early days of the universe. This was a turning point. The Hubble Deep Field, as the image came to be known, proved that even the quietest part of the sky was packed with ancient light. And the better our tools get, the further back we can go. With new instruments, especially ones that can detect infrared light, scientists began to look even deeper. Infrared is important because the oldest light has been stretched so much by the expansion of space that it no longer appears as visible light. Instead, it shows up in the infrared range, which our eyes can't see, but our telescopes can detect. The JWST, or JWST, launched years after Hubble, was designed with this in mind. Its large mirror and infrared detectors were built to catch the faintest, oldest light. And it's already finding galaxies from just a few 100 million years after the Big Bang. That might sound like a long time, but in cosmic terms, it's close to the beginning. We see them forming stars, gathering gas, merging with other galaxies. We're watching their early lives, long before they became the large spiral or elliptical galaxies we see today. The deeper we look, the younger the universe appears. Eventually, we reach a kind of wall, the point where the universe was so hot and dense that light couldn't travel freely. This moment, about 380,000 years after the Big Bang, is when atoms first formed and the universe became transparent. The light from this moment still exists. It fills the entire sky, though we can't see it with our eyes. It's called the CMB, or CMB, and it's the oldest light we can observe. This background light is like a baby picture of the universe itself. It shows us a time when everything was packed tightly together. Tiny changes in the temperature of this light helped seed the structures that would later become galaxies, stars, and planets. We've mapped this background in great detail using satellites like COBE, WMAP, and Planck. Each map brings us closer to understanding how the universe began and how it grew into what we see today. New telescopes on Earth, using giant mirrors and complex computer systems to sharpen their images, are preparing to search for the first stars, the very first sources of light in the cosmos. These stars were likely massive, bright, and short-lived. They helped shape the early universe, but they're too far and too faint to see with ordinary instruments. It may take years or decades, but someday we may finally catch a glimpse of them. And when we do, we'll be seeing a moment that happened over 13 billion years ago. The Great Limit: why the universe doesn't let us see forever. The universe is about 13.8 billion years old. That's how long light has had to travel. So, when we look out into space, the most distant thing we can ever hope to see is the light that has been traveling toward us for that long. Anything farther away simply hasn't had enough time to send its light to Earth. That light is still on the way, or hasn't even begun the journey yet. So we can't see it, and we may never be able to. This boundary is called the observable universe. It's like a bubble around us. From our position in space, the light from all directions forms a sphere of visibility. We are at the center, not because we are special, but because that's how observing works. Every place in the universe has its own bubble. If you were standing on a planet in another galaxy, your observable universe would be centered on you, but your view would reach a different set of galaxies, a different set of stars. The universe goes on beyond this limit, maybe forever, but we are locked inside the part we can observe. If the universe is 13.8 billion years old, shouldn't the farthest thing we can see be 13.8 billion light years away? That would seem to make sense, but it's not quite right. The universe has been expanding the entire time light has been traveling. That means the distance to the farthest galaxies we can see isn't just 13.8 billion light years. It's more like 46 billion light years. The light left those galaxies when they were much closer. But space has stretched since then, pulling those galaxies farther away. So even though we're seeing ancient light, the source of that light is now much more distant. This expansion is part of what makes the universe so hard to wrap our heads around. Space itself is growing. It's not that galaxies are flying through space like rockets. It's that the fabric of space between galaxies is stretching. This stretching carries galaxies away from each other, even if they aren't moving on their own. And it affects the light traveling across space too. The longer it moves, the more it gets stretched. If we want to look even further back, to the first moments after the Big Bang, we need something other than light. Some scientists are searching for gravitational waves that might have come from the earliest fractions of a second after the universe began. These waves, if detected, could give us a new way to see through the fog. But right now, they remain hidden. This built-in limit isn't just a challenge for telescopes. It's a fundamental part of reality. We can never observe beyond this cosmic horizon because of the nature of time, light, and space. It's like trying to hear a sound from before your ears existed. It's possible that the universe goes on far beyond what we can observe. In fact, most scientists believe it does. The part we can see is only a tiny slice. There may be regions of space with different galaxies, different clusters, even different physical conditions. But they are forever out of reach. The expansion of the universe is happening so fast that some regions are now moving away from us faster than the speed of light. That might sound like a contradiction, but it isn't. According to general relativity, space itself can expand faster than light without breaking the rules. And when that happens, light from those regions can never reach us. Not now, not ever. This means that some galaxies we see today may one day disappear from view. Their light will stretch and fade until it can no longer be detected. In fact, many galaxies are already beyond our reach. The light we see from them now left billions of years ago. And since then, the space between us has stretched so much that no new light will ever reach us. These galaxies are like ghosts, already lost to the growing dark. How photography freed the night sky from the human eye. For centuries, the telescope had one main user, the human eye. Even as telescopes grew bigger and more powerful, they still relied on a person looking through an eyepiece, trying to sketch what they saw before it faded. The sky revealed more than ever before, but it's still played by the limits of human vision. Our eyes are quick, but they're also weak. They can only take in so much light, and they tire easily. Faint stars, distant nebulae, and soft galaxies all remained hidden, too dim to leave a lasting impression on the eye. In the 1800s, photography arrived. At first, it was slow, clumsy, and difficult to use. Early cameras needed long exposure times and produced fragile images on glass or metal plates. But they had one major strength that the eye didn't. They could collect light over time. While your eye sees a moment and then moves on, a photographic plate keeps absorbing light the longer it's exposed. This meant a camera could stare at the sky for minutes, even hours, building up light from stars and objects that no human eye could ever see. The night sky was no longer limited to what a person could sketch or remember. It could now be recorded, studied, and revealed in full. The first real success came in 1840, when John William Draper, a scientist in New York, used a telescope to take a picture of the moon. It wasn't sharp or detailed by today's standards, but it proved the idea. You could aim a camera through a telescope and let the sky leave its own trace. Over the next few decades, others followed. Some of the earliest photographs showed star clusters and planets. One of the big breakthroughs came in 1880. Henry Draper, the son of John Draper, took a long-exposure photograph of the Orion Nebula. It showed a cloudy swirl of gas and stars far beyond what any eye could pick up through a telescope. The image was proof that photography wasn't just a tool for copying what people could already see. It was a tool for revealing things no one had ever seen before. With long exposures, astronomers discovered that space was full of faint objects, nebulae, galaxies, star-forming regions that simply couldn't be seen before. A telescope used with the eye might reveal a few stars in a certain patch of sky. That same telescope, paired with a photographic plate and a night of patience, would reveal hundreds. The longer the exposure, the more hidden light poured in. The universe began to grow deeper, layer by layer. Another key figure was Edward Charles Pickering at the Harvard College Observatory. In the late 1800s, he and his team of computers, many of whom were women, including Annie Jump Cannon and Henrietta Swan Leavitt, used photography not just to capture images, but to study the light from stars. By photographing spectra, the rainbows created when starlight was split by prisms or gratings, they could classify stars by type, temperature, and brightness. This work laid the foundation for modern astrophysics. One of the most important uses of photography in astronomy came in 1887 when an international project was launched to create a full photographic map of the sky. Called the Carte du Ciel, or Map of the Sky, this massive effort involved 18 observatories around the world. Over the next few decades, they took more than 20,000 photographic plates, each one capturing a different region of the heavens. It was the most ambitious project of its time. In 1890, the Harvard Observatory published the first volumes of the Henry Draper Catalogue, which classified stars by their spectra. These classifications, based on photographic plates, helped uncover a deeper structure in the cosmos. They revealed that stars were not just points of light, but physical systems with their own life cycles and properties. The true power of photography became even clearer when astronomers started noticing changes in the sky. Since photos could be stored and compared over time, it was now possible to spot variables, stars that changed in brightness, and even entirely new events, like novae or supernovae. If a star had exploded in a far-off galaxy, it might have been too quick or too faint to be seen by eye, but it would leave its mark on a plate, and that plate could be pulled from a drawer days or weeks later and studied at length. By the early 20th century, photography was the main engine of astronomical discovery. Telescopes were now being designed specifically to work with cameras. Large photographic telescopes were built to scan wide areas of the sky, each plate capturing tens of thousands of stars. Some observatories had entire teams dedicated to examining these plates, marking changes, measuring distances, and finding patterns. One of the most iconic examples of photography's power came in 1923. Astronomer Edwin Hubble used the 100-inch Hooker telescope on Mount Wilson to photograph a blurry object called the Andromeda Nebula. On one of his plates, he spotted a variable star, a Cepheid, whose changing brightness allowed him to calculate its distance. The result was staggering. Andromeda wasn't a cloud inside our galaxy, as many believed. It was its own galaxy, millions of light-years away. This one photograph broke the known universe wide open. What people thought was the whole of creation, the Milky Way, was now just one among countless galaxies. Space was vast beyond imagination. Long exposure photography also showed how messy and dynamic space really was. Dust lanes cut through galaxies like scars. Nebulae glowed in delicate reds and blues. Star clusters spilled across the sky like spilled salt. The universe was alive, textured, full of movement and light. Perhaps the most poetic part of this change was that photography didn't just help astronomers. It also let ordinary people see what was out there. A photograph could be published, copied, and shared. It could be printed in books and shown in museums. People who never owned a telescope, or who lived in cities too bright to see the stars, could now hold the sky in their hands. A single image could say more than 100 drawings. By freeing the sky from the eye, photography opened a new phase of exploration. But more than anything, it changed our relationship with the night. The darkness before light, what came before the first stars. After the light of the Big Bang was released, and the CMB began its long journey through space, the universe entered a strange and silent time. It had expanded and cooled enough for atoms to form, but stars had not yet appeared. The bright fireworks of creation had faded, and there were no new sources of light to take their place. For hundreds of millions of years, the universe existed in darkness. No stars, no galaxies, just cold hydrogen gas drifting through space. This was the time known as the Cosmic Dark Ages. It's a period that remains one of the most mysterious in the history of the universe. A long stretch of time between the last light we can detect from the early universe and the first light we can see from stars and galaxies. To find out what happened during this hidden chapter, astronomers have had to work like detectives, piecing together tiny clues, running computer models, and following the traces left in the structure of the cosmos today. During this time, the universe was filled with neutral hydrogen. These were atoms with a single proton and a single electron. After recombination, the moment when electrons and protons combined to form atoms, the photons that had once been trapped in the hot plasma were finally free to move. That's the light we see as the CMB. But once that light moved on, there was no new light to replace it. No stars had formed yet. Space wasn't completely black, but it was cold and quiet. This darkness was a calm before the storm. Gravity was at work in the background, slowly pulling tiny clumps of matter together. These clumps started out as slight differences in density, small ripples in the early universe. Some areas had just a little more matter than others. Over time, those areas pulled in more gas. As the universe expanded and cooled, these dense pockets grew. They were the seeds of future stars and galaxies, but during the Dark Ages, they were still invisible. The challenge of observing this time comes down to how we see the universe. Light is the messenger we use for almost everything. Whether it's visible light, radio waves, X-rays, or microwaves, we rely on photons to bring us information from space. But during the Dark Ages, there were no strong sources of light to send us those messages. The hydrogen gas was cold and neutral, and it didn't glow. There is, however, one signal from this time that astronomers have been trying to detect, the 21-centimeter line. This is a very faint radio wave produced by hydrogen atoms. Under very specific conditions, when the spin of the electron in a hydrogen atom flips relative to the spin of the proton, a small amount of energy is released in the form of a radio wave. It's incredibly weak, but because hydrogen filled the entire universe during the Dark Ages, it should have happened everywhere. If we could detect this signal, it would give us a map of hydrogen across space before the first stars formed. But detecting this signal is extremely difficult. Over billions of years, the 21-centimeter radiation has been stretched by the expansion of the universe. It's no longer at 21 centimeters. It's been stretched to longer wavelengths, now in the meter range. That makes it even weaker and harder to find. On top of that, Earth is filled with radio noise from human activity. Cell towers, satellites, radio stations, and even lightning can drown out the signal. To really study this Dark Age radio wave, we may need to go somewhere completely quiet, like the far side of the Moon, shielded from Earth's interference. Some experiments, like the EDGES project in Australia, are trying to detect the first hints of this 21-centimeter signal. In 2018, EDGES announced a possible detection of the signal from the time just before the first stars. The result was surprising and controversial. The signal seemed stronger than expected, which could mean something odd was happening back then. Maybe dark matter was interacting with the hydrogen in ways we don't yet understand. Or maybe there's something else entirely that we're missing. More data is needed, and other experiments are being built to double-check the result. Even though we can't see the Dark Ages directly, we know they must have happened. Without this quiet period, stars wouldn't have formed the way they did. Galaxies wouldn't have grown. It was during this time that the large-scale structure of the universe began to take shape. Filaments of gas stretched across space, forming the cosmic web. Dense nodes grew into galaxies. Gaps became the vast voids we see today. All of this happened in the dark. Eventually, the darkness ended. Somewhere in this deep silence, the first stars began to form, probably massive ones, burning hot and bright, made from pure hydrogen and helium. These stars lived fast and died young. But when they lit up, they changed everything. Their light began to break apart the hydrogen atoms in space, turning the neutral gas into charged particles once again. This era, called reionization, marks the beginning of the light-filled universe we know. But until that moment, the universe was a shadowy place, full of matter, motion, and potential, but without any real light. It's hard to imagine such a time because every view we have of space today shows stars, galaxies, and glowing clouds. But all of that had to come from somewhere. The cosmic Dark Ages were the waiting room for everything. The stars we now admire were being prepared during this time, hidden in darkness, shaped by gravity, and quietly getting ready to shine. The mystery of this era still pulls at astronomers. What were the first stars really like? How big were they? How many of them formed at once? Did they come together slowly, or did they burst onto the scene in great numbers? These are questions we can't answer yet. But as technology improves, and as we learn to listen for signals in ways we've never tried before, we might begin to unlock this hidden age of the universe. The faraway galaxies that shouldn't exist. According to current theories, galaxies take time to grow. After the Dark Ages ended, the first stars lit up and began to collect into small clusters. Those clusters merged and gathered gas, slowly building up into the large spiral and elliptical galaxies we see today. This process was expected to take hundreds of millions of years, even billions. But some of the early galaxies JWST has found were already large and bright when the universe was still in its infancy. These galaxies are strange in other ways too. Some appear to be very dense, packed with stars in small spaces. Others show signs of having well-formed structures, which shouldn't have had time to develop. In one case, astronomers saw a galaxy that looked so bright it would have had to form stars at a pace far beyond anything seen in today's universe. That's a red flag. If these galaxies are truly as old and massive as they seem, it means either we're wrong about how galaxies form, or something else entirely is going on. At first, some scientists thought there might be a mistake. Maybe the galaxies weren't as far away as they seemed. Distances in space are often estimated by looking at redshift, but redshift can be tricky, especially in early data. Other things like clouds of dust or certain star types can mimic the colors of distant galaxies. So follow-up studies began. In several cases, the results held up. Spectroscopic observations confirmed the extreme redshifts. These really were ancient galaxies, and their brightness and mass estimates remained high. The mystery deepened. Some researchers tried to adjust the models to see if early galaxies could grow faster than previously thought. Perhaps star formation in the early universe was more efficient. Maybe there were more dense regions of gas. Or maybe black holes and violent feedback loops helped accelerate the process. But each idea brings more questions. If galaxies formed this quickly, what does it say about the timeline of the universe? If large structures existed this early, it could mean our understanding of cosmic evolution is missing key ingredients. The standard model of cosmology, called lambda CDM or lambda cold dark matter, has done a good job explaining much of what we see. It describes how dark matter helps pull normal matter together, forming the skeleton of the cosmic web. It also accounts for the expansion of space, driven by dark energy. But it relies on the idea that things build up slowly. If galaxies grew faster than expected, it could mean that dark matter worked differently in the past, or that some other force was at play. Another possibility is that what we call the Big Bang timeline might need to be tweaked. Not the Big Bang itself, but the rate at which the early universe evolved. If the physics of the early universe were slightly different, if, for instance, expansion slowed down earlier than we thought, then structures would have had more time to grow. But that change would affect everything, from the formation of elements to the spread of CMB radiation. So far, the other pieces of the puzzle don't suggest a major mismatch. That makes the existence of these galaxies even harder to explain. Some scientists have even wondered if we're looking at something else entirely, objects that only look like galaxies but might be powered by black holes or bursts of energy. Maybe these are early quasars with bright disks of gas swirling around them. Maybe they're clusters of stars with strange properties. But these explanations feel like stretches. The observations are clear. We're seeing large, complex structures at a time when the universe was still very young. This isn't the first time something like this has happened in astronomy. History is full of discoveries that didn't make sense at first. When people first saw spiral galaxies, they didn't know what they were. When Edwin Hubble proved that galaxies lay far outside the Milky Way, it shattered the idea that our galaxy was the entire universe. Each time, the sky surprised us, and each time, it forced science to grow. That may be happening again. JWST is still in the middle of its mission. It's collecting more data, looking deeper, scanning wider patches of sky. The story of these ancient galaxies is still unfolding. Some might turn out to be closer than we think. Others may reveal unexpected chemistry or strange star populations. But it's likely that many are exactly what they seem, enormous galaxies that formed far too soon. This creates tension in cosmology. On the one hand, we have a model of the universe that works incredibly well on large scales. On the other hand, we now have observations that seem to break that model in subtle ways. Maybe the problem isn't with the theory itself, but with the assumptions we've made about the early universe. JWST has given us a new tool to test our ideas against the raw facts of reality. And reality is often stranger than we expect. We thought we had a timeline. But in those first few 100 million years, something happened. JWST has peeled back the curtain, and behind it, we are finding brilliant puzzles that reach across time to tell us that the story of the universe is not finished being told. The redshift frontier. What happens when light is stretched too far? Light travels in waves. Shorter wavelengths of light, like blue and ultraviolet, carry more energy and are easier to detect with visible light telescopes. But as the universe expands, the light waves coming from distant galaxies get stretched, making them longer and longer. Eventually they get stretched so far that they move out of the visible range entirely and into the infrared. Go farther still, and they end up in microwave or even radio wavelengths. This means that if we only use regular optical telescopes, we would completely miss much of the light coming from the distant universe. What was once bright and blue might now be dull and red, or even invisible to our eyes entirely. When we observe nearby stars or galaxies, the redshift is small, but when we look at galaxies billions of light years away, the light they've sent us has been stretched the entire time. This is why telescopes like JWST are designed to work in the infrared. But even infrared has its limits. There comes a point where the redshift is so extreme that light gets pushed out of even the infrared range. At the far edge of our cosmic horizon, galaxies might exist that we simply can't see anymore because their light has shifted too far for any current telescope to detect. This redshift frontier marks the boundary between what's detectable and what isn't. It's not a wall like the one caused by the CMB, it's more like a slow fade. The farther away something is, the fainter and redder it becomes, until finally it slips out of our view altogether. This makes the outer limits of the universe hard to define. Redshift also distorts how things look. A galaxy that once glowed with brilliant blue stars may now appear red and old. Its features may blur, its energy may seem lower. This can trick us into thinking a galaxy is older or colder than it really is. Astronomers have to work backwards, correcting for redshift, trying to figure out what the galaxy was truly like when the light first left it. In some cases, galaxies become so redshifted that even their hydrogen becomes invisible in traditional observations. Special techniques are needed to detect this lost light. Radio telescopes can help, as they pick up even longer wavelengths. But even then, some galaxies remain hidden. This stretching of light isn't just a nuisance, though. Redshift is one of the main pieces of evidence that the universe is expanding. Redshift became a ruler, a way to measure space, time, and the shape of everything. Over time, astronomers have mapped the redshift of thousands, then millions of galaxies. They've built three-dimensional maps of the universe, showing not just where galaxies are, but when they were. But it also reminds us that there's a limit to our vision. No matter how advanced our instruments get, redshift will always pull distant galaxies away from our eyes. How dust can trick our deepest eyes. When we look at pictures from deep space telescopes like JWST, we imagine we're seeing the universe as it really is. But there's a hidden layer in almost every image, and it's not made of stars or galaxies, it's dust. All across the cosmos, clouds of fine particles float between and around galaxies. These tiny bits of matter, often smaller than grains of sand, may seem harmless, but they can change the way we see the universe in subtle and powerful ways. Cosmic dust is made up of elements like carbon, silicon, and iron, often formed in the atmospheres of dying stars or in the aftermath of supernova explosions. Once released into space, these grains spread out and drift into vast clouds, sometimes collecting in large bands along the edges of galaxies or within nebulae. While the dust itself doesn't glow brightly like a star, it does interact with light, and that's where the trouble starts for astronomers. When light from a distant galaxy passes through these dust clouds, it can be absorbed or scattered. In some cases, the dust blocks visible light entirely, creating dark patches that look like empty space. In other situations, it dims or reddens the light. similar to how sunlight looks redder at sunset when it travels through more of Earth's atmosphere. This effect is called extinction and reddening, and it means the light reaching our telescopes has been altered, filtered by the space between. This presents a serious challenge when trying to figure out how old or distant a galaxy really is. A faint and red galaxy might be very far away. But if there's dust in the way, it could be a much closer galaxy that only appears that way because its light has been dimmed and shifted. Astronomers must be extremely careful not to mistake a dusty foreground object for a distant ancient one. To deal with this, astronomers use several tricks. One method is to observe the same part of the sky in different wavelengths of light, since dust affects visible light the most, but is more transparent to longer wavelengths like infrared. Switching to infrared gives a clearer view through the dust. That's one of the reasons JWST focuses on infrared. It's not just to see redshifted galaxies, but also to see through dusty regions that would block a visible light telescope like Hubble. Another method is to use models based on how dust behaves in galaxies we know well. By studying dust in our own galaxy and in nearby galaxies, scientists have built up a library of dust fingerprints. These models help them estimate how much light has been lost or changed due to dust. If a galaxy seems too red or faint, astronomers can use these fingerprints to correct the data, restoring a better guess at what the galaxy really looks like. But this isn't a perfect science. Dust doesn't behave the same way everywhere. Its properties change depending on the types of stars nearby, the chemical makeup of the galaxy, and how the dust has been shaped by radiation or shock waves. In the early universe, the first galaxies might have had dust that formed differently from what we see today, or in much larger or smaller amounts. That means our models, based on modern local galaxies, might not always work well on galaxies billions of years old. This is especially important when looking at the galaxies found by JWST that seem to be too big, too bright, and too old for their place in time. If dust is affecting the light from these galaxies, we might be misjudging their age or mass. A very dusty young galaxy could appear much older than it is, making it seem like it formed too soon after the Big Bang. Or a small galaxy hidden behind thick dust might look bigger because its light is spread out. If we're not careful, we might be seeing illusions rather than real challenges to cosmology. To sort this out, astronomers try to gather as much information as possible. They look at the spectra of galaxies to search for signs of dust. Specific patterns in the light, like absorption lines or thermal emissions, can reveal how much dust is present and what it's made of. The presence of glowing molecules like polycyclic aromatic hydrocarbons, or PAHs, can also hint at dusty regions full of star-forming activity. In some cases, astronomers combine data from different telescopes to get a fuller picture. For instance, they might use JWST's infrared data to see through the dust and then compare it with radio observations from telescopes like ALMA, which can detect coal dust directly. These cross-checks help confirm whether a galaxy is really as it seems, or whether dust is hiding something important. But even with these tools, there's still a lot of uncertainty. The early universe may have had types of dust we've never seen, formed under conditions we don't fully understand. Some theories suggest that the first stars could have created unusual types of dust during their deaths. If that's true, we might be underestimating or overestimating the dust content in these early galaxies, leading us to misunderstand what we're actually seeing. There's also the challenge of patchy dust, uneven clumps that affect parts of a galaxy differently. This can create strange effects in images, like parts of a galaxy appearing brighter or bluer than others. It can distort the apparent shape of a galaxy, making it look more chaotic or broken up than it actually is. Since JWST is finding many clumpy, irregular galaxies at high redshifts, there's a chance that dust is playing a bigger role than we thought in how these galaxies appear. Dust acts like a cosmic mask, and understanding how to read through this mask is one of the key challenges facing astronomers today. As our instruments become more sensitive and the galaxies we study get older and farther away, dust becomes more than just a background effect. Every photon that reaches us from the edge of the visible universe has made a journey through space. Learning how to read that journey and correct for the obstacles is what allows us to turn faint blurs into real insights about how the universe was born and how it grew. When you zoom too far, the lensing problem. Gravitational lensing is one of the universe's most useful tricks, and also one of its most misleading. At first glance, it seems like a gift. When light from a distant galaxy passes near a massive object, such as another galaxy or a cluster of galaxies, that light bends. It doesn't bend because of any physical barrier, but because gravity warps space itself. The massive object acts like a lens in a telescope, magnifying and stretching the light behind it. The result is that telescopes on Earth or in space can see things they otherwise couldn't. Faint and faraway galaxies get brought into view, sometimes made dozens of times brighter. In many cases, these lenses are the only reason we're able to study some of the earliest and most distant galaxies. But this lensing doesn't just make the light brighter, it also distorts it. Imagine looking through a wine glass at a candle. You might see the candle appear longer, or split into multiple copies, or even form a ring. The same happens in space. The light from background galaxies can be twisted into arcs, duplicated into mirror images, or smeared across the sky in ways that don't look anything like the original source. When astronomers are studying faint smudges of light from the edge of the observable universe, they often don't know if what they're looking at is the actual shape of a galaxy, or just a warped view. Sometimes lensing causes galaxies to look more massive or more luminous than they really are. A galaxy might appear unusually bright and compact, leading researchers to think it's an early cosmic monster that formed just a few 100 million years after the Big Bang. But if lensing is in play, that same galaxy might actually be much smaller and fainter, and it could be from a more recent time. Without knowing how much lensing is affecting the view, scientists can overestimate the galaxy's size, age, or star formation rate. Figuring out whether a galaxy is being lensed, and by how much, isn't always easy. Sometimes the signs are obvious. The galaxy forms a near-perfect arc, or a ring-like shape called an Einstein ring. These are clear clues that lensing is happening. But other times, the distortions are subtle. They might be hidden among other galaxies, or the lensing mass itself might be too faint to detect directly. In those cases, researchers have to rely on models. They simulate what the sky would look like with and without lensing, and try to match that to the real data. It's a lot like working backward from a funhouse mirror image to figure out what the original object looked like. JWST is so powerful that it regularly captures galaxies at the very edge of visibility, objects that could be lensed or not, and it's hard to know which. Some of the most striking early JWST images, such as those from galaxy clusters like SMACS 0723, are filled with arcs and swirls, visual fingerprints of lensing. These clusters are not just beautiful, they're cosmic magnifying glasses, and with them come all the challenges. Scientists have started building detailed lensing maps of these regions. They track the mass distribution of galaxy clusters and try to calculate how each portion of the sky bends light. This involves adding up the mass of every galaxy, guessing how much dark matter might be sitting around them, and using equations from general relativity to estimate the bending of space. It's a lot of work, but without it, measurements can't be trusted. There's also the issue of strong lensing versus weak lensing. Strong lensing creates those dramatic arcs and multiple images. Weak lensing is harder to spot. It subtly stretches and distorts the shapes of background galaxies across large portions of the sky. When astronomers average out the shapes of thousands or millions of galaxies, they can detect this weak lensing signal and use it to learn about dark matter, dark energy, and the structure of the universe. But for individual galaxies, weak lensing adds a layer of fuzziness that's hard to correct. It makes everything just a little harder to interpret. One surprising twist is that gravitational lensing doesn't just affect images, it also affects time. Light that travels around a massive object can take slightly longer to reach us than light that takes a straight path. This time, delay can be measured in some cases, such as when we see multiple images of the same distant supernova or quasar. The light from these copies arrives at different times, sometimes days, sometimes even years apart. This strange time warping effect can actually help astronomers measure the expansion rate of the universe, but again, only if the lensing is carefully modeled. Another complication comes from galaxies that are both lensed and redshifted. It can be tricky to untangle which part of that signal comes from the galaxy's actual age and composition, and which part comes from the lensing effect. Astronomers have to work through every detail, including whether dust or other foreground features are adding to the confusion. Some of the deepest puzzles in current astronomy, including the discovery of galaxies that seem too big, too old, or too bright to exist so soon after the Big Bang, might be linked to lensing. It's possible that some of these oddball galaxies are simply more ordinary galaxies caught in a lens. To manage all this uncertainty, researchers use software that can simulate thousands of possible lensing scenarios and run comparisons with real telescope images. They test how different mass distributions would bend the light. They compare multiple wavelengths, and when possible, they look for lensing patterns that show up in other parts of the sky. With enough time and data, they can estimate how reliable a galaxy's brightness or size actually is. Even so, there's always a margin of error. Some galaxies may be misclassified. Some may look like early cosmic giants, only to turn out much less dramatic. Others might be overlooked altogether because they're stretched too thin or blurred into shapes that don't catch the eye. That's the paradox of lensing. It helps us see more, but it also hides and twists what we're seeing. Gravitational lensing gives us a way to peer deeper into space, but to truly understand what we're seeing, we have to unravel the distortion. We have to reverse engineer the lens. Only then can we hope to see the universe as it really was, not just as it appears through warped glass. The oldest galaxy ever seen. In one of JWST's deep field surveys, the telescope found something remarkable, a galaxy catalogued as MOM-Z14, whose light has traveled across more than 13.5 billion years of space and time. By the best measurements, this galaxy existed just 280 million years after the Big Bang, placing it among the earliest known cosmic structures, almost like a fossil snapshot of the universe's youth. At first glance, MOM-Z14 might seem exactly what astronomers expected from a galaxy of this era: faint, distant, and extremely redshifted. But when its spectrum was examined, the data showed something that broke the simple picture of early galaxy formation. This ancient system didn't just contain hydrogen and helium. It carried the unmistakable fingerprints of heavier elements like carbon and nitrogen. The implication was profound. The stars inside MOM-Z14 were not the very first generation. Some had already lived, burned, exploded, and enriched the surrounding gas with these heavier elements, long before this galaxy formed. This changes the story of the early cosmos in important ways. For one, it means that the first stars must have formed and died far earlier than we thought. These population 3 stars would have been the first to turn nuclear fusion into heavier elements. If MOM-Z14 already had measurable amounts of carbon and nitrogen so soon after the Big Bang, those stars must have come and gone within a cosmic blink of an eye. It compresses the timeline of stellar birth, evolution, and chemical enrichment into a very tight window. For such a young galaxy, it appears surprisingly massive, hinting that star formation in the early universe may have been more rapid and efficient than models suggest. This echoes other recent JWST findings. In the modern universe, heavy elements spread through gas clouds gradually as generations of stars live and die. But for MOM-Z14 to have detectable amounts so early, the process must have been incredibly fast and violent. Perhaps the first stars were so massive that their supernova explosions were far more energetic, ejecting enriched material across vast distances. Or maybe early galaxies were much more dynamic, with intense bursts of star formation followed by equally intense feedback. winds and radiation that quickly mixed the chemical products into the interstellar medium. The detection itself relied on both the sharp imaging of JWST and the ability to analyze light through spectroscopy. The fact that these signals were strong enough to measure across such a vast gulf of space speaks to just how powerful the telescope is, and how lucky we are to live in an age when such measurements are possible. MUM-Z14 is, in some ways, not just a galaxy, but a message. Its light carries information from a time when the universe was less than 2% of its current age. Every photon we detect from it began its journey before our planet, before our sun, before even the Milky Way existed in its present form. Looking at this galaxy collapses basically the entire age of the universe into a single image. We are not just observing a faraway patch of sky, we are seeing a place that has been frozen in time since long before anything familiar in our own corner of the cosmos took shape. Before JWST, we simply could not see this far, this clearly. Now, in just the first few years of JWST's operation, we are rewriting the early chapters of cosmic history. MUM-Z14 is likely not alone. Other galaxies of similar age and composition are probably out there, waiting to be found. Each will add another piece to the puzzle of how the first structures formed, how they lived, and how they seeded the universe with the elements that would eventually make life possible. MUM-Z14 belongs to a time so far removed from ours that it is hard to imagine the conditions in which it existed. Yet, the fact that it already contained elements like carbon, the same element that makes up the backbone of all known life, ties it to us in a subtle way. In a sense, we are seeing the distant beginnings of the chemical story that would one day allow Earth, plants, animals, and people to exist. The giant eyes that will follow JWST. Even though the JWST is the most powerful observatory ever launched into space, it's not the end of the story. It's just the beginning of a new era of astronomy. For decades, astronomers have worked with telescopes that steadily improved over time. As soon as one telescope reaches space, scientists are already dreaming of what comes next. And today, those dreams are starting to take shape in the form of even bigger, smarter, and more capable observatories. Some of them are being built on Earth. Some are being prepared for space. All of them are designed to push the limits even further than JWST can. One of the most anticipated next-generation observatories is the Nancy Grace Roman Space Telescope, often just called the Roman Telescope. It's being built by NASA and is expected to launch near the end of this decade. At first glance, Roman might not seem all that different from Hubble. In fact, it has a similar mirror size, about 2.4 meters wide. By comparison, JWST's mirror is 6.5 meters wide. But what sets Roman apart is how much sky it can see at once. Hubble and JWST both focus on small, detailed patches of space. Roman, by contrast, has a field of view that's hundreds of times larger. It can scan vast regions of the sky in a single shot, like going from a microscope to a wide-angle lens. This wide view is a game-changer. Roman will be able to survey huge numbers of galaxies, stars, and planetary systems at once. That means it can find patterns that JWST can't. While JWST might zoom in on a few early galaxies in detail, Roman could map entire populations of galaxies across cosmic time, helping us understand how structure formed in the universe on a large scale. It will also be a powerful tool for discovering exoplanets, using a technique called microlensing to spot distant worlds that are otherwise invisible. But Roman isn't alone. Back on Earth, astronomers are preparing telescopes so large and complex they would have seemed like science fiction just a few decades ago. One of these is the Extremely Large Telescope, or ELT, under construction in Chile. The name might sound a little on the nose, but it's accurate. This telescope will have a mirror nearly 40 meters across, made up of almost 800 hexagonal segments, working together as one enormous surface. That's more than 5 times the size of JWST's mirror, and it will gather more than 15 times the light. Because it's on Earth, the ELT has to deal with the atmosphere which blurs images and distorts light. But modern technology can correct for this. The ELT will use adaptive optics, a system of lasers and mirrors that adjust in real time to cancel out the blurring caused by Earth's air. This gives it the ability to produce incredibly sharp images, in some cases even better than JWST's. It won't be able to see in quite the same deep infrared range that JWST does, but in the near-infrared and visible bands, it will be unmatched. With instruments designed to study everything from exoplanets to dark matter, the ELT is meant to be a true general-purpose observatory. It will be able to zoom in on planets around other stars and analyze their atmospheres, searching for chemicals like oxygen and methane that could be signs of life. It will also be able to look deep into space and time, studying the light from ancient galaxies that formed soon after the Big Bang. The goal is to connect the big picture, how the universe evolved, with the fine details, what individual stars and planets are made of. Another powerful eye being built is the 30-meter telescope, or TMT, also planned for the southern hemisphere. Like the ELT, the TMT will have an enormous segmented mirror, in this case 30 meters wide. It will also use adaptive optics and focus on similar goals, helping astronomers study distant galaxies, black holes, and alien worlds. Having multiple giant telescopes on Earth isn't redundancy, it's reinforcement. Different locations offer different views of the sky, different observing conditions, and allow for around-the-clock science as the Earth rotates. Together, the ELT, TMT, and others form a network of giant eyes that will scan the skies from the ground. But what about space? Even with all the technology on Earth, nothing compares to observing from above the atmosphere. That's why astronomers are already thinking about the next flagship space telescope after JWST. One of the top candidates is called LUVOIR, which stands for the Large UV/Optical/Infrared Surveyor. LUVOIR is still in the planning stages, but its proposed designs are ambitious. The smallest version would have an 8-meter mirror, already much bigger than Hubble or Roman, and the larger version could be 15 meters wide, more than double the size of JWST. LUVOIR would be a true all-in-one machine. It would study planets, stars, galaxies, and the structure of the universe. It would look for biosignatures, gases that hint at life, in the atmospheres of Earth-like planets. It would map the structure of the Milky Way in stunning detail. Its ultraviolet instruments would detect clues that other telescopes can't see, and its sharp vision would allow it to study exoplanets directly, separating their faint light from the glare of their stars. Another proposed telescope is HABEX, short for the Habitable Exoplanet Observatory. As the name suggests, it's designed with one primary goal in mind: to find habitable worlds. Unlike LUVOIR, which is broad in scope, HABEX is more focused. It would specialize in studying stars like our Sun and searching for planets that orbit in the right zone, not too hot, not too cold, where liquid water could exist. HABEX would carry a special companion, a star shade, a giant disk that would fly thousands of kilometers ahead of the telescope to block out starlight and let the telescope see the much fainter planets nearby. All of these future telescopes are part of a larger journey. Astronomy is a chain of tools, each one building on the last. JWST is giving us our first sharp look at the early universe. Roman will zoom out and show us how widespread those strange galaxies are. The ELT and TMT will zoom in again, studying them in detail. LUVOIR or HABEX could then tie those details back to the question of life and structure across the universe. Each telescope answers questions and raises new ones. What's clear is that we're not stopping. The more we see, the more we want to see. And now that we've gotten our first real glimpse of what lies at the edge of everything, we're building bigger and better tools to go even further. Just as JWST was a leap beyond Hubble, the next generation will leap beyond JWST. And if the universe has taught us anything so far, it's that every time we look deeper, we find something stranger and more beautiful than we expected. The orbiting monoliths. Could we build a telescope bigger than Earth? JWST, incredible as it is, uses a mirror that's just over 6 meters wide. That size limits how much light it can collect, and how detailed its images can be. It's like trying to take a picture of a grain of sand from across a stadium using a small handheld camera. But if you make the mirror wider, much, much wider, then your picture gets clearer. You can see finer features, fainter objects, smaller things farther away. The problem is, we can't just build a mirror the size of Earth and launch it into space. It's not remotely feasible with today's rockets, and even if it were, keeping something that large, stable and pointed would be nearly impossible. That's where a clever trick comes in, a trick called interferometry. Interferometry is the idea of combining multiple smaller telescopes, spread out over a great distance, so they act like one giant telescope. Instead of one big eye, you use many small ones working together. If you place them far apart and combine their signals correctly, you get the same sharpness as if you had one big mirror stretching between them. We already use this trick on Earth. Radio telescopes like those in the Very Large Array in New Mexico, or the network that helped take the first picture of a black hole, the Event Horizon Telescope, work this way. They're built from dishes that are spaced miles or even continents apart. But doing this in space would be an entirely new level. Imagine putting a telescope on one side of the Moon's orbit and another on the opposite side, or putting dozens of telescopes in a line stretching across Earth's orbit around the Sun. Suddenly, you're seeing details that no telescope today could even dream of. One of the most talked about future missions using this method is a project called the Large Interferometer for Exoplanets, or LIFE. The idea is to launch multiple infrared telescopes into space and fly them in formation. By carefully syncing their observations, scientists could cancel out the light from stars and isolate the much dimmer light of orbiting planets. It would be like turning down a spotlight just enough to see the firefly buzzing next to it. That kind of clarity is more than just nice. It's necessary. If we want to study planets around other stars, we need to see them not just as tiny points of light, but as real places. Places where we could search for clouds, or oceans, or signs of life in their air. Interferometry could allow us to see those details for worlds that are dozens or even hundreds of light years away. Another wild concept is something called the hypertelescope. Instead of one mirror or dish, it would be an array of mirrors flying in space in a precise pattern. These mirrors wouldn't form one surface, but would work together like scattered pieces of one huge, invisible lens. The idea was first suggested by French astronomer Antoine Labeyrie, and in theory, it could produce images sharp enough to see continents on alien planets. The engineering challenges are massive, keeping everything aligned while floating in space, dealing with vibrations, shielding from solar radiation, managing fuel and power. But the concept keeps drawing attention because the payoff is so big. There's also the orbiting rainbows idea, not an official name, but a poetic one. It comes from a concept called star shades, where a giant flower-shaped shield is flown thousands of kilometers in front of a telescope to block the light of a star. With that glare out of the way, the telescope behind it can clearly see the planets orbiting the star. Pairing this method with an interferometer could give us both the light filtering and the resolution needed to directly image Earth-like planets, and maybe even their weather systems. All of these future tools share something in common. They're more than just bigger versions of old telescopes. They're using entirely new methods of seeing. They treat space itself as part of the instrument. They use formation flying, precise timing, and optical tricks to build virtual telescopes that are wider than any structure we could ever build physically. And some designs go even further. There are papers exploring the idea of using swarms of microsatellites, each the size of a toaster, working together in tight coordination to form reconfigurable telescopes. If one satellite drifts, the others adjust. If a section needs repairs, a few satellites can be replaced. This makes the system flexible, expandable, and more resilient than any single monolithic telescope. There's also growing interest in using the Moon itself as a base for giant telescopes. The far side of the Moon is naturally shielded from Earth's radio noise. That makes it a perfect quiet zone for building a huge radio telescope. maybe even one that stretches across a crater. If we ever get a lunar base up and running, this could be one of its first scientific missions. Building on solid ground rather than floating in space would bring some advantages in terms of stability and maintenance. But whether in space, on the moon, or around the sun, all these concepts are pointing in the same direction. We're hitting the limits of what one telescope can do alone. To go further, to see finer, to explore deeper, we have to start thinking bigger, much bigger. That means working across distances, combining instruments, and treating space itself as part of the machine. There's something poetic about that. It means our tools for looking outward are starting to resemble the universe they're trying to understand. Large, distributed, full of pieces working together. Telescope by Star, the Solar Gravitational Lens Project. Far out in the solar system, more than 500 times the distance between the Earth and the Sun, lies a strange and powerful region of space. Taking advantage of the fact that the Sun can gravitationally lens light, this bending can be used to construct a gigantic natural telescope. This idea is known as the Solar Gravitational Lens Mission, and while it sounds like something from science fiction, it's rooted in real physics and actual mission design plans. The Sun's gravitational field bends light coming from behind it, curving it inward toward a central axis that stretches far into space. If you place a camera or sensor along that axis, at just the right distance, which starts around 550 astronomical units, or AU, light from a distant object behind the Sun will focus there, forming a thin, magnified ring. With the right equipment, it would be possible to collect that light and reconstruct an image of whatever object lies behind it. The scale of magnification is staggering. The Sun's gravity doesn't just bend light a little. It warps it in a way that theoretically allows for up to a trillion-fold magnification. That's enough to image the surface of an exoplanet tens of light-years away in kilometer-scale detail. Instead of just detecting a tiny dot of light and measuring its spectrum, we could potentially build an actual image of the planet, clouds, oceans, continents, maybe even signs of technology or vegetation if they're there. The project has been described by some scientists as the most powerful telescope humanity could ever build without building anything big, just by placing a small spacecraft in the right place. The technical challenges are huge. To get to 550 AU would take decades with current propulsion technology. The Voyager 1 spacecraft, which launched in 1977 and is the most distant human-made object, has only just passed 160 AU after nearly 50 years of travel. Getting to the focal point of the solar gravitational lens would require new methods to reach the necessary speed. The mission would also require extremely stable positioning. The spacecraft would need to hover in a region barely tens of kilometers wide while tracking a target light-years away, while also blocking the Sun's direct light from overwhelming the faint signal. Another major challenge is the distortion of the image. The light that reaches the solar gravitational lens doesn't form a normal flat picture. Instead, it's warped into a ring. To reconstruct a proper image, a spacecraft would have to move sideways across that ring, slowly collecting data from different angles, and then use advanced algorithms to reverse the distortion and form a coherent picture. It's not like snapping a photo with a camera. It's more like slowly reading the grooves of a vinyl record, one point at a time, and then reconstructing the music from the shape of those grooves. Despite these hurdles, teams from NASA and other research institutions have seriously tried to map out what a solar gravitational lens mission would require. A conceptual study called Focal has already laid out the early mission design. There are ideas to pre-launch multiple probes, working together or as backups. They might use small, lightweight materials and carry only essential instruments. Once far enough from the Sun, the spacecraft could deploy small shielding disks to block solar glare and begin searching for target alignments. The kind of targets they're interested in are not random stars or galaxies. They're specific exoplanets that have already been identified by missions like Kepler or TESS. planets that orbit in the habitable zone of their stars, and where telescopes like JWST have picked up potential signs of atmospheres, water, or interesting chemicals. The idea is to choose just one or two of these planets and design a long-term mission to fly out to the gravitational lensing point and observe them directly. That way, instead of guessing what's happening on these worlds, we could actually see them. Some versions of the mission concept propose launching by mid-century, perhaps as part of a larger push toward deep space exploration. If propulsion technology advances fast enough, such as by using solar sails powered by lasers, the time to reach 550 AU could be brought down from decades to under 20 years. That would make the mission more feasible within a human lifetime. Scientists involved in early studies say the science return would be unmatched by anything else. A chance to directly observe other Earth-like worlds, possibly even looking for continents, oceans, storms, or city lights. But even beyond planets, a solar gravitational lens mission could be used for a wide range of deep space science. Its ability to collect light over vast distances could let it peer into the most ancient parts of the universe, detect dim galaxies, or even look for signs of cosmic background ripples. It's like unlocking a tool that nature has already built. We just need to get into the right place to use it. Some compare the project to the idea of a cosmic microscope. Instead of building a giant optical system on Earth or in orbit, we use the curvature of space-time itself, created by the Sun's gravity, to do the focusing for us. In a way, it's the ultimate lens, one that doesn't wear down, doesn't break, and doesn't need maintenance. Of course, as with all large space projects, the road from concept to reality is long. Budget, political interest, and competing priorities may slow things down. And there are still unknowns, like how much solar interference will affect the signals, or how easily spacecraft can hold position so far from the Sun's warmth and power. But the growing interest in exoplanets, especially those that might resemble Earth, gives the idea momentum. With each passing decade, the desire to actually see other worlds, not just detect them, but look at them, becomes stronger. Instead of always building more hardware, sometimes we just need to understand how nature works and find clever ways to use it. Gravity, light, and distance, these forces already shape the universe. Now, perhaps they can help us explore it more clearly than ever before, putting a telescope at 550 AU. Reaching 550 AU away from Earth is not just an engineering challenge, it's a stretch of the imagination. That distance is far beyond the Kuiper Belt and even beyond the Oort cloud's inner edge. It's a place where sunlight is just a dim glow, where communication signals take more than 3 days to travel one way. Getting there, and making it work, pushes us to the edge of everything we know about spaceflight. If we sent a Voyager-style spacecraft today, it would take around 150 years to get to 550 AU. If we want to build something useful in a human lifetime, we need to go much faster. Solar sails are large, thin sheets that catch the pressure of sunlight, just like wind in a sailboat, to push a spacecraft forward. The closer the sail gets to the sun, the stronger the push. Some proposals suggest diving very close to the sun, letting the sunlight give a powerful shove and using that boost to fling the spacecraft outward. With the right materials and timing, some simulations show we could reach 550 AU in 25 to 30 years. Another possibility is electric propulsion. Ion drives that slowly but steadily build up speed over years. These engines don't give the kind of instant push a rocket does, but they're much more efficient. NASA's Dawn mission and the European Space Agency's Bepi Colombo both use this kind of system. Scaling it up for deep space travel would require careful planning, a lot of power, and a spacecraft that could stay functional for decades. Whichever method is chosen, the spacecraft will have to be tough. At 550 AU, space is harsh and cold. The solar panels we usually rely on won't work well because sunlight is too weak. Instead, the spacecraft would need to carry its own power, probably using a radioisotope thermoelectric generator, like the one on Voyager or the Mars rovers. But even those decay over time, so every watt of energy has to be used wisely. Systems must be highly efficient, and the entire mission has to be designed for extreme endurance. Then there's the question of navigation. The spacecraft has to arrive in a very precise location. The gravitational lens effect only works if the object, the Sun, and the spacecraft are perfectly lined up. That means we need incredibly accurate maps, powerful navigation software, and mid-course correction systems that can work over decades. Once the spacecraft gets to the lensing point, it can't stop. It has to keep moving further out, because the focal region of the Sun's gravity is not a point, but a line that stretches out behind the Sun. As it moves, it would scan along that line, collecting different pieces of the target image. Scientists believe that with the right instruments, it could eventually combine these slices into an incredibly detailed picture. That brings up another major challenge: data. Special software would be needed to untangle these patterns and turn them into useful pictures. A spacecraft that far away would have to send its data back across 550 AU, more than 80 billion kilometers. A message would take over 3 days to reach Earth, and because of the distance, it would be incredibly faint. To catch it, we'd need very large antennas on Earth, or perhaps even a network of receivers working together. That's a challenge of its own, but one that deep space missions have slowly been preparing us for. A mission like this takes decades. That requires a different mindset, one that's focused on legacy and the long arc of discovery. It's the kind of thinking that built cathedrals or planted trees whose shade would only be enjoyed by future generations. It's hard to justify in a world focused on short-term rewards, but space exploration has always been about patience. Telescopes made of nothing but light. Unlike normal glass lenses, which bend light through their shape and thickness, diffractive optics work by using extremely fine patterns etched onto a surface. These patterns manipulate the path of incoming light by taking advantage of the way light waves interact. In some designs, these patterns could be printed onto ultra-thin films, as thin as a soap bubble, that could be launched into space, tightly folded, and then unfurled like a giant sail. Once expanded, they would act as lenses that could focus light from distant galaxies and exoplanets, but weigh a fraction of what a mirror or lens would. The benefit here is clear. When launching things into space, weight is expensive. Every gram adds to the fuel and cost. Mirrors like those used in the Hubble or JWST are heavy and need a lot of structural support to hold them in place. Diffractive optics, on the other hand, could float almost freely, shaped and stabilized by the slightest push, sometimes even by light itself. This leads to another fascinating idea: using lasers or sunlight to form or control the shape of the lens. This is known as photonic engineering, and it's still in very early stages, but the potential is enormous. There's a related concept that goes even further: optical meta-surfaces. These are surfaces engineered at the level of atoms, with structures so small they can control the phase and direction of light in precise ways. With meta-surfaces, you don't even need a curved lens to bend light. You can do it with a flat surface, one that's carefully designed to make light behave as if it passed through a traditional lens. This means that the future of telescopes might involve flat sheets of material that can act like giant focusing eyes, without the bulk or complexity of traditional designs. In space, these sheets could be unfolded like origami, or even printed directly by machines already in orbit. Then there are ideas that push the concept of light-based optics to its most extreme version: telescopes that use laser-formed lenses. Imagine firing a set of lasers into empty space in just the right configuration. The crossing beams could create a lens out of nothing, just an area in space where light gets bent in a certain way. This isn't something we can build yet, but the basic physics isn't impossible. Under the right conditions, light can shape the space it passes through, especially if it's moving through a medium like plasma or even atoms cooled to near absolute zero. In the far future, this could let us build a telescope that doesn't need any solid parts at all, just fields of energy, shaped and aimed from a distance. But even without going that far, we're already seeing versions of this idea in development. For instance, one proposal called MOIA, or Membrane Optical Imager for Real-Time Exploitation, was designed by DARPA as a kind of space-based telescope made of folding membranes. It would use a series of lightweight diffractive lenses to collect and focus light, creating high-resolution images of Earth or deep space. While MOIRI hasn't flown yet, it shows how this approach could work. Other versions involve inflatable structures, think giant space balloons, that act like lenses or mirrors when shaped correctly. These could be built on the ground, launched folded up, and inflated once in orbit, stretching out into enormous telescopic arrays. One big advantage of using these light-based or membrane-based designs is size. With solid mirrors, you eventually run into limits. How big can you make it before it breaks under its own weight or becomes too difficult to launch? With light materials or optics formed by light itself, you can dream much bigger. Telescopes with collecting areas the size of football fields or even football stadiums. These could detect fainter signals from farther away than anything we've ever built. Signals from the first stars, or perhaps from alien civilizations. Some designs imagine fleets of these structures flying in formation, acting together like one massive lens. Interferometry is used in radio astronomy, but in the future, it might work with optical or infrared light too, giving us a kind of artificial eye the size of the Moon's orbit. Still, these dreams come with challenges. Making sure a lightweight lens keeps its shape in space isn't easy. Vibrations, temperature changes, and even tiny impacts from micrometeoroids could shift or damage the structure. Controlling something made of light or ultra-thin material requires precise guidance systems, sometimes involving tiny thrusters or magnetic fields. And interpreting the data from these new kinds of telescopes would take software that can handle strange distortions or signals unlike anything we've seen before. There's also the question of how to aim a telescope made of flexible material or laser fields. Traditional telescopes move with motors and gears, but something that bends like a sail or changes with energy might need a whole new way of pointing at targets. Some researchers suggest using electric fields to tweak the shape of the lens, like muscles flexing in response to a signal. Others imagine adjusting the power and angle of laser beams to shift the whole focus of the system, like steering with sunlight. All of this suggests a very different future for astronomy, one where we don't just build bigger telescopes, but stranger ones. Instruments that look more like sails, membranes, or light sculptures than anything we'd call a telescope today. But their goal remains the same: to gather faint signals from across the universe and to bring us closer to answers about where we come from. As we begin to master the strange behavior of light and learn how to bend it without glass or mirrors, we open a new era in our view of the cosmos. An era where our telescopes may become as invisible as the mysteries they seek to reveal. The observable universe isn't the whole universe. Some scientists have tried to estimate how much more universe there might be beyond the observable part. Depending on the models, it could be hundreds, thousands, or even trillions of times larger than what we can see. If the universe is infinite, then anything that can happen might happen. Not just once, but many times. There could be other Earths, other galaxies that look just like ours, even copies of you reading this right now. These are logical consequences of certain cosmological models. They're extreme, but they follow the math. Others are more cautious. They say we can't assume what we can't observe. The universe might be infinite, or it might be shaped in a way we haven't yet imagined, a curve so gentle that it only looks flat to us. Maybe it loops back on itself over vast distances, like a giant sphere or torus. If that's the case, then perhaps the universe is finite but unbounded. You could fly in a straight line forever and end up back where you started, never hitting an edge. But even if that's true, the size of the loop would be far larger than our observable bubble. The observable universe is our window, but it's not the whole house. It's not even the whole street. We live inside a patch of the cosmos that we've learned to map in incredible detail. yet beyond it lies an ocean of uncertainty. Still, humans are not good at accepting boundaries. Every time we run into one, we try to push past it. That's what telescopes have always done, not just to magnify, but to reveal what was once thought unreachable. So now some scientists are looking for ways to stretch the edge again, not by moving the limit of the observable universe, which we can't do, but by using clever tricks, like quantum measurements or strange statistical methods that might hint at what lies beyond. There's also another approach, looking for echoes. If something big happened in the far-off universe, like a strange pattern in the CMB, it might leave a trace inside our visible patch. Some cosmologists think these could be signs of other universes, or different domains in a larger multiverse. If such a trace were found, it wouldn't show us what's out there, but it would suggest that out there exists in a real and active way. All of this leaves us in a strange place, surrounded by more questions than answers. We can map the galaxies, measure the redshifts, watch the light curve around clusters and fade into background radiation. But we can't see beyond the cosmic curtain. We know the play doesn't end at the edge of the stage, but we don't know what scenes are unfolding off-screen. Could wormholes be cosmic telescopes? A wormhole is a theoretical structure in space-time. It's often imagined as a shortcut between two very distant places. Instead of traveling across billions of light-years through space, you could jump through a wormhole and arrive almost instantly on the other side. In sci-fi, wormholes are used to travel across the galaxy in seconds. But in real physics, they are an open question. They could exist, but we've never seen one, and we don't know if they can be made stable enough to use. Still, they show up in solutions to Einstein's equations. That means, at least mathematically, they are allowed by general relativity. The big challenge is figuring out whether nature actually builds them, and if it does, whether anything could pass through safely. But let's say, for the sake of argument, that wormholes are real and usable. Could we use one to see something we otherwise never could? In normal space, we're stuck looking only as far as light has had time to travel. That's why we can't see beyond the edge of the observable universe. That's where wormholes enter the picture in an interesting way. Imagine a wormhole whose opening lies somewhere near Earth. Now suppose that the other end of that wormhole opens somewhere far beyond our observable universe. If the wormhole is stable, and if we could send light through it, or receive light from the far end, then we might be able to see what lies beyond the cosmic horizon. In theory, we could peer into a region of space that, by every other method, is out of reach. The wormhole would act like a telescope, but one that doesn't rely on light traveling the normal path through space. Some physicists have asked if wormholes exist, could light pass through them? And if it can, what would the image look like when it comes out the other side? It turns out that this question leads to all kinds of new puzzles. Light that bends through a wormhole doesn't follow a straight path. Its journey is curved and strange. That means the image we see might be warped or compressed. Shapes could be distorted. Colors might be shifted. Even time itself might appear to behave differently depending on how the wormhole curves space. Some simulations have tried to model what you'd see when looking through a wormhole. In most of them, the image you get is circular, like looking through a peephole. Around the edges, the view bends, and you can sometimes see behind and around objects, because light is wrapping through the tunnel in multiple ways. In the center, you might see a clear view of a world that lies unimaginably far away. If that faraway place was a galaxy, you could see it as it is now, not just how it looked billions of years ago. You could bypass the normal delay that light has when traveling through space. That alone would be incredible. One of the major limits of cosmology today is that we're always looking into the past. But if wormholes let us look across space without that time delay, we might finally get a look at galaxies not as they were, but as they are right now. It gets even more interesting when you consider the possibility of peering into a completely separate region of the universe, a place that formed with a different arrangement of matter, different galaxies, maybe even different physical properties. If the wormhole's other end opened into a part of the universe that had different conditions than ours, we might see what the cosmos is like beyond our cosmic bubble. And that could help answer deep questions about whether the universe is truly uniform on the largest scales, or whether we just live in a tiny patch that looks smooth and regular. There are also more speculative ideas. Some theories of the universe suggest that other bubble universes might exist. Parallel regions of space with different constants, different particles, or even different laws of physics. If wormholes could somehow connect not just distant places in our own universe, but places across these cosmic domains, then the telescope becomes something much stranger. It would no longer be just a window across space. It would be a window across possible realities. That's an enormous leap, and it depends on whether our universe allows for those structures at all. Right now, we just don't know. But even sticking to our own universe, the use of wormholes as observational tools would mark a complete shift in how we do astronomy. All our current instruments rely on collecting light that has traveled across space. With wormholes, light could take a shortcut. We might see things out of sequence, looking at events that haven't yet happened from our perspective. This would raise questions about causality, about time, and about how information travels through the cosmos. In some versions of the theory, wormholes can even act like time machines. If that's true, then looking through one might not just show us a distant place. It might show us a different moment in time, possibly the future or the past. Wormholes are tricky to handle mathematically. Some require forms of exotic matter to stay open, types of material with negative energy which haven't been observed in nature. Others close too quickly or collapse when anything tries to pass through. But not all models are doomed. Some suggest that wormholes could exist at quantum scales, or that they might emerge under certain extreme conditions, like near black holes or in the early universe. One idea, still very new, is that entangled particles, the kind that show up in quantum experiments, might be connected by tiny wormholes. If true, that could mean there's a deeper relationship between space, information, and connectivity. In that case, wormholes wouldn't just be weird tunnels in space. They might be a basic feature of how the universe is built. We're already dreaming of gravitational lenses, interferometry, and other tools that stretch our reach. But if wormholes are real, and if we can figure out how to use them safely, they could change everything. They could turn the cosmos into something more connected, not just in space, but in time, and even between worlds that we can't currently reach. Neutrino eyes. Neutrinos are among the strangest particles in the universe. They are almost massless. They carry no electric charge, and they pass through normal matter as if it isn't there. At any given moment, trillions of them are streaming through your body, mostly coming from the sun, without you feeling or noticing a thing. They are so elusive that the name ghost particle has become almost standard in describing them. But while this might make them sound unhelpful for astronomy, the truth is the exact opposite. In fact, their very ability to slip through matter without scattering makes them perfect messengers from places that light itself cannot reach. Beyond the CMB, in terms of photons, the universe is hidden from view. But neutrinos, being electrically neutral and incredibly non-interactive, could pass through that hot plasma almost unhindered. If we could detect them well enough, they could let us look back to the very first seconds after the Big Bang, eras of cosmic history that are invisible to light. Neutrinos already have a long history in astronomy. We have used them to study the sun's nuclear reactions directly, confirming that it produces its energy through fusion. We've detected bursts of neutrinos from supernova explosions, giving us a way to watch the inner collapse of a dying star before the shockwave becomes visible in light. But these are just hints of what could be possible. Imagine if our telescopes were sensitive not just to photons across the electromagnetic spectrum, but also to vast numbers of neutrinos arriving from across the universe. In a way, it would be like giving astronomy an entirely new sense, one that could pierce through opaque walls and reveal hidden events. The biggest obstacle is that neutrinos interact so rarely with matter that we need extreme measures to detect them. Current neutrino observatories, like the IceCube Neutrino Observatory buried deep in the Antarctic ice, rely on cubic kilometers of detection medium just to capture a few events. A neutrino will only very occasionally collide with an atomic nucleus, producing a flash of light or a trail of secondary particles that can be recorded. For neutrino astronomy to open the truly ancient chapters of the universe, we would need detectors many times larger and more sensitive than anything we have today. If such technology existed, it could let us see the cosmic neutrino background. This is the neutrino counterpart to the CMB, but formed even earlier. These relic neutrinos were released when the universe was less than 1 second old, almost unimaginably close to the moment of creation. They carry information about the extreme conditions at that time, including the density, temperature, and composition of the young cosmos. Detecting the cosmic neutrino background would be like finding the fingerprints of the very laws of physics operating at their most extreme. It could reveal whether the universe expanded smoothly from the Big Bang or passed through exotic transitions, such as brief phases dominated by strange forms of matter or energy. It could even hint at entirely new particles or interactions that we've never seen in a laboratory. Even without going that far back in time, neutrino eyes could transform our view of cosmic events. For example, the earliest generations of stars and galaxies were often enshrouded in dense gas and dust. These materials can block most wavelengths of light, but not neutrinos. We could watch star formation happening inside thick clouds long before their first light could escape. We could witness black holes forming in the cores of collapsing stars, seeing the moment of their birth instead of the delayed fireworks of their aftermath. We could even monitor the collisions of neutron stars and black holes from deep within their debris, tracing the processes that generate heavy elements like gold and platinum. Neutrino astronomy could also help answer one of the deepest puzzles in physics: why there is more matter than antimatter in the universe. The very early cosmos should have produced both in equal amounts, which would have annihilated each other, leaving behind nothing but radiation. Yet here we are, living in a universe made almost entirely of matter. Some theories suggest that subtle differences in how neutrinos and antineutrinos behave in the first fractions of a second could have tipped the balance. To test this, we'd need to capture neutrino signals from that era and analyze them in detail. From a practical standpoint, building neutrino eyes that can see the entire universe is a monumental engineering challenge. We would need detection volumes perhaps the size of small planets, or innovative new materials that can dramatically boost interaction rates without requiring impossible amounts of matter. Some researchers imagine using natural planetary bodies as detectors, reading out faint signals caused by neutrino collisions deep underground. The day we open these neutrino eyes, our idea of the beginning of the universe might change forever. We might find that the first second after the Big Bang was far more eventful than we imagined, full of exotic phenomena that light will never be able to tell us about. Or we might discover that our current models were wrong in fundamental ways, forcing a rewrite of cosmic history. Either way, the ghost particles that slip silently through us every second could one day become our most important guides to understanding where everything began. Seeing with something other than light. There are places light can't go, or if it does, it gets so bent, scattered, or absorbed that by the time it reaches us, it doesn't tell us much. But the universe doesn't speak in light alone. There are other messengers, and over the last few decades, we've learned how to listen to them. Predicted by Einstein over 100 years ago, gravitational waves are created when massive objects move in extreme ways. Imagine two black holes spiraling into each other and merging. The force of that collision doesn't just send out energy, it shakes space-time like a pond hit by a stone. Those ripples travel outward at the speed of light, and when they reach Earth, they're so faint that they stretch and compress space by less than the width of an atom. For decades, these waves were purely theoretical. No one thought they could ever be measured. But in 2015, scientists using the LIGO observatory did just that. They detected a tiny tremor in space caused by the collision of two black holes more than 1 billion light-years away. It was the first time in history that humanity had observed the universe not through light, but through gravity itself. Gravitational waves have opened a new window on the cosmos. They don't get blocked by dust or clouds. They don't scatter. They carry information about the most violent and mysterious events in the universe. Things like neutron star crashes, black hole mergers, and possibly even echoes from the very beginning of time. And as detectors become more sensitive, we'll be able to hear fainter and more distant signals. These are not just new observations. They're a completely different kind of vision. Together, neutrinos and gravitational waves are helping to build a new kind of astronomy, sometimes called multi-messenger astronomy. The idea is to look at the universe with as many senses as possible. Use light, yes, but also particles, gravity, and anything else that can carry a message across space. When a single event is seen in both light and gravitational waves, or light and neutrinos, it gives us a fuller picture. It's like watching a silent movie versus hearing the sound, too. There may be other messengers waiting to be discovered. Some scientists think there could be particles even more elusive than neutrinos, ones that barely interact with anything at all, but still carry energy and information. Others imagine strange fields or forces that could ripple across the cosmos. The history of science suggests that every time we build a new kind of instrument, we find something we never expected. Entire worlds of knowledge can open up from a single breakthrough. There's also dark matter. Its gravity holds galaxies together, bends light, and affects how the universe expands. If we could find a way to detect particles of dark matter directly, not just through their gravitational pull, but through some kind of new interaction, it could change everything. It would be like discovering a new sense. It's easy to forget that what we call seeing is just one way of knowing. It works well on Earth, where light reflects off trees, water, people, and animals. But space isn't Earth. If we want to understand the universe in full, we need to think beyond the eye, and even beyond the telescope. The cosmos has many voices. Is there a way to see faster than light? Is there any way to cheat the speed of light? Could we observe something without having to wait for its light to crawl all the way to us? One of the oldest ideas proposed in physics to break the speed of light is the tachyon, a hypothetical particle that always moves faster than light. Tachyons, if they existed, would never be able to slow down below light speed. They would be the opposite of everything we know. According to special relativity, they would carry imaginary mass. Not imaginary as in fake, but imaginary as in numbers involving the square root of -1. Mathematically, that doesn't break any rules, but it's a strange way to describe something real. For decades, physicists have searched for any trace of tachyons in cosmic rays or particle accelerator data. So far, there's nothing. Still, the idea of faster-than-light communication or observation won't go away because the possibilities are so huge. Imagine if we had a way to detect changes in a galaxy the moment they happened. No delay, no time lag. It would be like turning the universe into a live feed. You could monitor a supernova in real time, or even watch how a black hole's surroundings change as matter spirals in. But for any of this to happen, we'd need a kind of signal that could travel faster than light. Not just a particle, but a method of moving information. And that's where the real problem lies. In physics, sending information faster than light usually leads to paradoxes. If you could send a message that arrives before it was sent, then cause and effect get twisted. You could warn yourself of something before it happens, or prevent something that caused the message to be sent in the first place. This opens the door to logical contradictions, the kind that break the foundations of our understanding of time. Many physicists argue that this is why faster-than-light communication is impossible. But there are ways around the strict rules, at least in theory. One idea involves quantum entanglement, the behavior Einstein once described as spooky action at a distance. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. This seems like it could be used to send messages faster than light, but in reality, it can't. You can't control the outcome of the measurement, which means you can't use it to transmit information. The link is real, but it's more like a shared randomness than a signal. Another idea comes from the world of curved spacetime. If space itself can expand faster than light, which it did during the early inflationary period after the Big Bang, then maybe we can use that feature in reverse. What if you could create a kind of bubble where space contracts in front of you and expands behind you? This is the idea behind the Alcubierre drive, sometimes called a warp drive. It doesn't move faster than light in the normal sense. Instead, it moves by distorting space itself. You wouldn't be moving through space faster than light. Space itself would be doing the moving. If such a drive were possible, then a telescope mounted on it could, in theory, reach places far faster than a beam of light ever could. You could send it across thousands of light years and get it to the destination in a human lifetime. It could collect data up close, then use the same drive to return. But this too is still just theory. The Alcubierre drive requires negative energy, something we don't know how to create or contain. And even if we could, building a stable warp bubble is a challenge no one knows how to tackle. There's also the idea of hypothetical particles or fields we haven't discovered yet, things that might exist outside the standard model of physics. If the universe has more dimensions than we can perceive, then it's possible that some form of energy or signal could move through those hidden dimensions in a way that bypasses our speed limit. It's like thinking in 2 dimensions and trying to imagine how something could move through a third. From our point of view, it might look instantaneous, even though it follows rules we don't understand. These are just ideas at this point, but they're being explored in string theory and other extensions of current physics. Even if we never find a way to truly see faster than light, we might still cheat the system in clever ways. One method could involve setting up a vast network of telescopes across space, slowly launched over decades or centuries. Each one would observe a different part of the sky and send its data back using normal light speed signals. The trick here is that the telescopes would already be in position. You wouldn't have to wait for the light from a distant galaxy to reach Earth, because the telescope would be out there, waiting for the light to reach it. This wouldn't give you real-time observation of everything, but it could greatly expand how much of the universe we can watch as it evolves. Can entanglement transmit images from afar? You can separate entangled particles by kilometers or even across satellites in orbit, and their shared behavior remains perfectly linked. But could we actually use that connection to send or receive information instantly? Could we one day transmit not just a signal, but an entire image, a picture from across the universe, using quantum entanglement? If it worked, we wouldn't need giant mirrors or kilometers-long antennas. We could see what's happening on a distant world in real time. It would be 2 points in space, connected by quantum rules, passing pure information from one to the other. But the deeper you go into the science, the more complicated that dream becomes. When 2 particles are entangled, their properties, like spin or polarization, are undefined until one is measured. The instant you measure one, you also determine the state of the other, no matter how far away it is. But that instant correlation doesn't transmit anything useful by itself. You can't control what result you get when you measure the first particle. It's random. The second particle's result will match in a certain way, yes. But there's no way to control it or use it like a message. It's like opening 2 envelopes that always contain matching numbers, but you can't decide what number to write inside before sealing them. This limitation is why entanglement by itself doesn't break the speed of light or allow instant communication. If you want to use it for something practical, like sending an image from a telescope in another galaxy, you'd need a way to control what the particles say to each other. And that's what modern physics says you can't do. Still, researchers haven't given up. Some scientists are trying to build experiments where entangled particles are used alongside classical communication channels. In those setups, you might not send the whole image through quantum entanglement, but you could use it to transfer part of the data, like encryption keys or timing signals, with perfect security. That's one of the big ideas behind quantum communication. You send entangled photons between 2 places, and even if someone tries to intercept the signal, you'll know because the entanglement gets disturbed. That's very useful for secure networks on Earth or between satellites. But it's not quite the same as sending a photograph from an alien world. There's also the more exotic idea of quantum teleportation. That name sounds exotic, but it's a real technique that's been demonstrated many times. Here's how it works. You entangle two particles, A and B. Then you bring in a third particle, C, which holds the information you want to send. You do a special kind of measurement involving A and C, which destroys them both, but transfers the quantum state of C to B. The end result is that particle B, possibly located far away, now behaves exactly like C did. It's as if C has been teleported across space. But again, there's a catch. You still need to send classical information alongside the process, and that travels at the speed of light. So even though the quantum part looks instant, the whole thing is still bound by light speed limits. But what if, somehow, those limits could be overcome? That's where things move from mainstream physics into speculation. Some theories suggest that space and time are just surface-level features of a deeper quantum reality. If that's true, maybe entanglement isn't happening through space, but outside of it. In that case, maybe distance doesn't matter at all, and perhaps with the right approach, the barriers we face now could be sidestepped. Imagine, for instance, a system where two telescopes, one on Earth and one in deep space, are entangled at the quantum level. They'd be sharing quantum states, maybe pixel by pixel, without photons actually crossing the vast gulf between them. If such a system could be made to work, it wouldn't be just a new kind of telescope. It would be a whole new way of looking. To be clear, we don't know how to build such a thing. The theories are exciting, but they're not complete. Quantum mechanics is still full of mysteries, and the limits of entanglement, especially when it comes to using it for communication, are tightly bound by rules we don't yet fully understand. Some argue that those limits are fundamental, baked into the very structure of physics. Others believe we're just scratching the surface, and that future technologies might find clever ways around them. Even if entanglement can't send full images, it might still be useful for helping telescopes work better. Imagine an array of space telescopes, each paired with entangled sensors, working together like one giant eye. They could compare signals in ways that classical instruments never could. That kind of system could sharpen images, reduce noise, and allow for much finer detail when studying distant galaxies or exoplanets. We're already seeing hints of this in quantum-enhanced sensing. Some labs are exploring ways to use entangled light to beat the diffraction limit, which is the fundamental barrier to how sharp an image can be. If those techniques scale up, future space telescopes could use quantum tricks to see things today's instruments miss. You wouldn't be sending an image instantly across the galaxy, but you might be making images that are far clearer, more precise, and full of structure that was invisible before. Would a mirror in another galaxy work? When we look at a galaxy that is 10 billion light-years away, we're seeing it as it was 10 billion years ago. But what if the universe could return the favor? What if, somewhere far away, there was a giant cosmic mirror? And what if, by looking into it, we could see our own galaxy as it used to be? The laws of physics make something like this possible, at least in theory. If a giant reflective surface, natural or artificial, existed in a distant part of the universe and reflected light back toward us, then that light would carry an image of what was in front of the mirror long ago. That could include us, or at least our galaxy, maybe even our solar system, depending on the size, angle, and position of the mirror. Because of the enormous distances involved, the reflection would act like a time machine, showing us a younger version of ourselves from billions of years in the past. But where would this mirror be? And what could it be made of? Nothing like it has ever been observed. Natural mirrors don't really exist on this scale, but space is full of objects that reflect or scatter light. Dust clouds, ice particles, and even galaxy clusters can reflect or bend light in complex ways. Some have proposed that dark matter, if it interacts weakly with light, could possibly reflect or echo radiation in odd ways. Others imagine an alien-built structure, something the size of a planet or larger, placed far out in space to serve as a signal or beacon. Such a structure might reflect starlight, or even produce its own directed light beam. Would we ever be able to see the reflection? The light from our galaxy would have had to travel billions of light years to hit the mirror, and then billions more to return. That means the reflected image would be even older than most of the galaxies we currently observe. If we could see it, we might be looking at the Milky Way not as it was when the dinosaurs walked the Earth, but as it was before the Earth itself formed. A ghost of our galaxy from a time before our solar system existed. Even if the physics lines up, there are extreme challenges. For one, the mirror would have to be aimed just right. If it were even slightly off, the reflected light would miss us entirely. And it would have to be big. Not just large by human standards, but by cosmic ones. A mirror the size of the moon, placed a few light years away, wouldn't be nearly enough. It would have to be many light years across, more like a galactic scale surface, and precisely positioned. The reflected light would be incredibly faint after such a long journey. Picking it out from the background glow of the universe would be like trying to hear a whisper in the middle of a hurricane. It would require a telescope beyond anything we have. Still, the idea opens a strange door in our imagination. We can't send messages faster than light, but we can watch ancient signals arrive. A cosmic mirror, whether a cloud, a lensing object, or some kind of alien artifact, could reflect not just light, but history. It could allow a civilization to see itself as it once was, long after it has changed or disappeared. Some have even wondered whether gravitational lensing could act as a kind of warped mirror. In rare alignments, this can create multiple images of the same object, like an echo of light. In theory, light from Earth that passed by a distant galaxy and was bent back toward us could return millions or billions of years later. These lensing loops are difficult to form and even harder to detect, but they aren't impossible. If one were discovered, it could let us see our own planet in deep time, like looking into the past through a trick of gravity. Could someone else already be looking at us this way? If an alien civilization built a mirror or a giant lensing array far away in space and angled it toward Earth, they might be watching our history unfold in real time, delayed only by the speed of light. They could be seeing ancient Earth, maybe even the earliest stirrings of life. From their perspective, our present hasn't happened yet. In fact, if we ever do build extremely powerful telescopes and aim them back toward areas of space where our own past light might have reached, it's possible we could spot reflections of ourselves. In those distant signals, we might not see Earth or human beings, but the early Milky Way, a galaxy still swirling into form, shaped by collisions and gas clouds and newly born stars. It would be a strange sort of self-portrait, painted by the universe itself using light we didn't even know we sent. Cosmic repetition. Are we seeing the same galaxies twice? If you were standing in a room full of mirrors, you'd see your own reflection bouncing off walls, over and over, stretching into what seems like infinity. Now imagine that happening not with mirrors, but with entire galaxies. Not in a room, but across the fabric of the universe itself. This is the idea behind cosmic repetition. The possibility that the shape of the universe might cause light to travel in such a way that we see the same galaxies more than once, from different angles or at different times. This concept comes from an area of study called cosmic topology. Topology, in basic terms, is the study of how things are connected and shaped. In everyday life, we don't often think about the shape of space. We assume space goes on in all directions. But just because we experience space this way doesn't mean it actually behaves like that on the largest scales. The universe could be finite but unbounded, like a torus. In such a universe, if you could travel far enough in one direction, you might eventually return to your starting point. But light, which also travels through space, would behave the same way. If space is curved or loops back on itself, a beam of light from a distant galaxy could travel around the universe and reach us again from another direction, making it seem like a different object. Or more precisely, we might see that same galaxy repeated across the sky, sometimes millions or even billions of years apart in its evolution. Some research teams have scanned the sky, looking for signs that certain galaxy patterns repeat. They search for similarities in shape, light spectra, and age, anything that might suggest we're looking at duplicates. If the same piece of the universe shows up more than once in different parts of the sky, it might mean that space is curved or connected in some way. The universe is not only vast, but constantly evolving. A galaxy we see in one place might look slightly different if we see it again, just because time has passed and stars within it have moved or died. On top of that, galaxies can look very similar by chance. Many spiral galaxies look almost the same to our telescopes, and distinguishing true repeats from lookalikes is a major challenge. Another complication is cosmic inflation, which stretched out space so much that even if the universe was curved or wraps around, the distances involved might be far too great for light to have made the full journey yet. That means the repeating images might exist, but they're still on their way. Or maybe they've been stretched beyond our cosmic horizon. But suppose the universe is small enough and the light has had time to wrap around. What would that mean? It would change how we understand the size and shape of everything. Instead of thinking of the universe as an endless stretch of new galaxies, we'd have to accept that it's more like a hall of mirrors, a finite space giving the illusion of infinity through clever light tricks. It would also mean that our map of the universe is misleading. Some of the millions of galaxies we see could be echoes, not originals. We might have much less matter in the cosmos than we think, just seen many times over. That has implications for everything, from how we model galaxy formation to how we estimate dark matter and dark energy. If we're counting the same galaxies multiple times, even unknowingly, it could affect the numbers we base our theories on. This is why cosmic topology, despite sounding abstract, matters deeply to our understanding of space. There's also a philosophical side to all this. If we live in a repeating universe, it hints at a kind of cosmic symmetry. The universe might not be random chaos spread endlessly outward, but something with structure and form, something that, on some deep level, folds back on itself like a grand equation. A place where the end connects to the beginning, where the past might be visible from the future. Mathematicians have come up with many different possible shapes the universe might take. Some are simple, like the torus mentioned earlier. Others are far stranger, spaces where if you travel in a straight line, you not only loop around, but flip upside down or appear mirrored. These exotic shapes are hard to picture, but can be described with math. Each shape has its own unique signature, and scientists hope that by comparing those models to real data, like the distribution of galaxies or the patterns in the CMB, they might find a match. Interestingly, in 2003, a pair of researchers proposed that the universe might be shaped like a dodecahedron, a 12-sided object like a geometric die. They suggested that the CMB showed hints of this shape, with matching circles on opposite sides of the sky. Their theory sparked excitement, but further measurements with more precise satellites didn't confirm the pattern. Still, it opened the door to other similar ideas, and the search for cosmic repeats continued. If one day we do find that certain galaxies show up in more than one place in the sky, that some light has traveled the full round trip of the cosmos, it would be one of the most profound discoveries in human history. It would mean we've not only looked into the past, but into a deeper truth about reality. That space isn't just a stage for the universe, but an actor in the story too. What we expect to find just beyond the horizon. What do we expect to find just beyond the edge of what we can see? The first guess is the most natural one, more of the same. In fact, the pattern of the cosmos doesn't suggest that it ends at the visible edge. It's smooth, consistent, and roughly the same in all directions. This kind of smoothness is called isotropy, and it tells us that there's no reason to think our corner of the universe is special. We don't see a hard edge or a drop-off as we reach the limit. The universe just continues like an ocean stretching into fog. One of the tools scientists use to support this idea is something called the cosmological principle. It's the assumption that the laws of physics, and the general structure of the universe are the same everywhere. And even though we can't prove that for places we can't see, we can test it within our visible range. And so far, it holds. That means that if galaxies are arranged a certain way here, they're probably arranged similarly just past the horizon. If the CMB has tiny ripples here, it probably has similar ripples out there too. That lets astronomers build models, mental and digital simulations, of what should be waiting for us in the dark. But the truth is, we're still guessing, and that makes things interesting. Because even though the most likely answer is more of the same, some scientists have asked, what if it's not? What if beyond our light horizon, the universe is different in some deep way? Maybe the laws of physics bend a little, maybe the strength of gravity changes, or the charge of the electron, maybe the fine structure constant, a number that controls how atoms behave, is slightly different, changing chemistry, the way light interacts with matter, even the color of stars. That would mean other parts of the universe could look very different, even though they're made of the same building blocks. There are models that suggest that inflation could have created bubbles of space. Other bubbles, still expanding beyond our view, might have different settings. On the largest scales, the universe has a web-like pattern, galaxies and clusters tied together in filaments with huge voids in between. It looks like foam, or the structure of neurons in a brain. This cosmic web stretches across billions of light years, and yet it's still forming. Galaxies are still merging, clusters are still growing. Gravity is still at work, even in the distant reaches. So what's the pattern just beyond the part we can see? Simulations of dark matter suggest that the web doesn't stop. It goes on, with the same mix of density and emptiness, structure and randomness. But some models also allow for large, possibly rare structures, things we haven't seen yet, like supervoids bigger than any we've found, or megaclusters beyond comparison. There could even be regions where matter is spread more thinly, changing the local shape of space-time. And if dark energy behaves differently in those regions, it could create strange distortions. Another possibility, more speculative but fascinating, is that something ancient lies beyond the edge, a kind of fossil from before the CMB. Some theories suggest that if the universe had a phase before inflation, some imprint of that era might exist in the form of unusual energy patterns or temperature anomalies. If we ever reach beyond the light horizon, we might stumble into that forgotten era, frozen in the silence of space. Every time we build a better telescope, every time we gather more light, we add a pixel to our cosmic picture. And by studying the way light bends, stretches and shifts, we can sometimes infer things just out of view. In a way, the universe lets us cheat, gives us clues about what lies beyond, without showing it directly. So the question remains, what do we expect to find just past the horizon? More stars? Yes, more galaxies, certainly. But also, maybe, a different version of everything. Or maybe it's just more of us. An infinite reflection. Signs of a multiverse hidden in deep sky data. In 2007, scientists studying data from the WMAP spacecraft found something odd in the CMB, a large cold spot, much colder than the areas around it. This cold spot covers a region of space hundreds of millions of light years across and doesn't have a clear explanation. Some researchers suggested it might just be a statistical fluke, a rare patch of space that just happened to turn out that way. But others offered a more dramatic idea. Maybe it's the scar from a collision between our universe and another one. If universes really are born like bubbles in a larger space, then they might sometimes bump into each other as they expand. The result could be a kind of bruise on the fabric of our universe, a region where the temperature, structure, or direction of space has been affected by this contact. When the Planck satellite launched and began taking even more detailed measurements of the CMB, scientists looked again at the cold spot. The data confirmed that the cold spot is real. It's not an error or noise. But they still couldn't agree on what caused it. Some teams looked for signs of voids, large, empty areas of space that could affect light as it passes through. Others ran simulations to test whether a bubble universe collision could leave exactly that kind of imprint. In addition to the cold spot, there are other patterns in the sky that have raised eyebrows. One of them is the so-called axis of evil, a strange alignment of temperature fluctuations in the microwave background that seems to point in a particular direction. This is unexpected. The early universe should be more random. Some researchers have suggested this alignment could also be a trace of interaction with something beyond our universe, though again this is very speculative. Another possible clue lies in gravitational waves. If our universe ever did collide with another one, the shock could send ripples through space-time, the same kind of waves we now detect from merging black holes. These multiverse waves would be much older and subtler, but some scientists think they could be found in future, more sensitive gravitational wave detectors. In theory, they might even carry a kind of fingerprint from the other universe, its size, shape, or structure. The multiverse idea shows up naturally in several major theories of physics. The trouble with the multiverse is that it's very hard to test. By definition, most other universes would lie beyond our cosmic horizon. But if they leave behind indirect evidence, then maybe, just maybe, we can learn that they're there. Of course, extraordinary claims require extraordinary evidence. A cold spot could be caused by a void. An alignment might be a coincidence. A strange wave could come from some entirely unknown source inside our own universe. And yet some physicists continue to argue that if we keep finding things that don't quite fit our models, and if these same models naturally predict the multiverse, then maybe we're closer to the truth than we think. Even if we never see another universe directly, the possibility changes how we think about our own. If we're one bubble among many, then perhaps our universe's laws are not the only possible laws. Maybe the constants of nature are just one version out of many. That could help explain why they seem so perfectly tuned for life. In a multiverse, it's not surprising that we find ourselves in one of the few universes where life is possible. The others simply don't have observers asking these questions. Are we part of something unimaginably vast, where every possibility plays out somewhere? Or are we alone in a single, unique creation? The answer may lie in the sky, not in the places we've already studied, but in the faint, forgotten corners, the cold spots, the ripples, the misalignments. Holographic horizon hypothesis. Imagine if the universe in all its vastness, with its galaxies, nebulae, and endless void, was not what it appeared to be. Imagine that the deep black sky full of stars was, in a sense, a kind of image, a projection, something that exists because of information stored somewhere else. This is the essence of the holographic horizon hypothesis. It suggests that the reality we see, 3 dimensions of space and 1 of time, might be a kind of shadow cast from a more fundamental lower dimensional surface. To picture this, think of a regular hologram on a credit card. The surface itself is flat, just 2 dimensions, but when you tilt it, you see a 3D image floating above it. The hologram doesn't contain the object itself, but it encodes all the information needed to recreate the image from different angles. The holographic horizon idea works in a similar way, except on a cosmic scale. The surface, in this case, could be the boundary of our universe, or at least the boundary of the observable part of it, storing all the information that describes everything inside. The first seeds of this idea came from black hole physics. In the 1970s, scientists like Jacob Bekenstein and Stephen Hawking were studying how black holes store information. They found that the amount of information a black hole can contain, its entropy, is not determined by its volume, as you might expect, but by the area of its event horizon. That is, the surface of a black hole tells you how much information it can hold. This hinted that perhaps information about 3-dimensional space might be fully stored on a 2-dimensional boundary. Later, physicists Gerard 't Hooft and Leonard Susskind took this idea and expanded it into the holographic principle. They proposed that not only black holes, but perhaps the entire universe might operate on this rule. that the deepest level of physical reality could be described in terms of data living on a cosmic boundary. Our universe, with its apparent depth and volume, would be a projection of that underlying information. The horizon in the holographic horizon hypothesis is often compared to the cosmological horizon. If the holographic principle applies here, all the information about everything we can see might be encoded on this distant spherical boundary, much like how a planet's surface can hold a map of everything that happens inside. If the hypothesis is correct, then our familiar three-dimensional world, full of depth and distance, might not be the most fundamental layer. It could be like the image in a movie, vivid and rich, but ultimately made from something simpler. This doesn't mean it's an illusion in the everyday sense. The movie is still real, you can still interact with it, but its structure comes from somewhere else. Testing such an idea is not easy. It's not the kind of thing you can just build a telescope for. Instead, researchers look for tiny clues in the fabric of reality that might betray its holographic nature. One example is the search for pixelation in space-time. If space itself is made from information stored on a two-dimensional surface, there might be a smallest possible unit of space and time, a fundamental resolution. And under the right conditions, we might detect slight noise or blurring from this limit. Experiments like the Fermilab holometer were designed to search for such effects, using extremely sensitive laser interferometers to see if reality jitters at the tiniest scales. So far, no clear sign has been found, but that does not mean the idea is wrong. It might be that the scale at which these effects appear is far beyond our current reach, or that the signs are more subtle than we know how to detect. Another pathway for testing comes from high-energy physics, especially in string theory. String theory naturally incorporates the holographic principle in certain cases, most famously through something called the ADS-CFT correspondence, a mathematical duality discovered by Juan Maldacena in 1997. This correspondence shows that a certain kind of universe with gravity can be exactly equivalent to a different kind of universe without gravity, living in one fewer dimension. If such dualities apply more broadly, it could mean that our own universe has a holographic twin description on a cosmic boundary. The implications are enormous. It would mean that the structure of space and time is not fundamental, but emergent, like waves on the surface of water, beautiful, complex, but ultimately built from something deeper. And if time itself emerges from a lower dimensional description, it could change how we think about beginnings, endings, and the Big Bang itself. If everything we perceive is the result of information encoded elsewhere, then our role as observers becomes more like decoding a message than directly touching reality. Every galaxy we see would be part of a vast, interconnected pattern projected into our experience from the cosmic edge. In a way, it might solve one of the biggest puzzles in physics: how to reconcile gravity with quantum mechanics. Gravity works best in the smooth, continuous spacetime of Einstein's relativity, while quantum theory thrives in discrete, probabilistic interactions. If the universe is holographic, then gravity might just be a large-scale effect emerging from more fundamental quantum information processes on the boundary, sidestepping the direct clash between the two frameworks. Of course, this idea has its critics. Some physicists caution against taking the holographic analogy too literally, arguing that while it is a powerful mathematical tool, it might not describe our real universe. Others point out that until we have clear experimental evidence, it remains a fascinating but unproven speculation. Still, the holographic horizon hypothesis offers a way to bridge deep theoretical gaps while also sparking the imagination. It invites us to think about the universe not just as an ocean we swim in, but as a kind of vast and intricate code stored on a surface we may never directly touch, yet which defines everything we know. If it's true, then when we look out into the night sky, we're not just seeing light from ancient stars. We're also glimpsing the unfolding of a grand projection, one that began with the first moments of the universe and continues to this day, playing out in a space that might be, at its core, flatter and stranger than we can yet comprehend. The ultimate deep field. If we had unlimited time and tech, We've already gotten a glimpse of this idea with the Hubble Deep Field and the James Webb Deep Field. Those images, captured over several days or weeks, revealed thousands of galaxies hiding in what once looked like nothing at all. Each tiny point of light turned out to be an entire galaxy, full of stars, planets, and unknown histories. It shocked even the scientists who planned the observations. But those images are limited by time and by technology. If we had none of those limits, we could push deeper still. The first thing we would notice is how the picture slowly becomes richer and more complex. The longer we stare, the fainter light we collect. The oldest galaxies would slowly appear, one by one, like faint stars emerging at dusk. Eventually, the entire field would glow with countless galaxies, each one a city of stars in a universe that no longer looks empty. But it wouldn't stop there. Our perfect telescope would not only collect visible light, it would see in all wavelengths. That means we could look at things that are completely invisible to human eyes. Cold gas clouds glowing in the radio band, supernova remnants flickering in X-rays, baby galaxies still forming inside thick cocoons of dust, visible only in the infrared. The field would become a multi-layered portrait where every slice of the spectrum adds new information. Not just about where things are, but how they behave, what they're made of, and how they've changed over time. And then we would see motion. With perfect tools and unlimited time, we wouldn't just take a still image. We'd watch the sky like a time lapse. Black holes would light up as they consumed nearby gas. The sky would no longer be static. It would pulse, shift, and grow like a living thing. Eventually, as our view deepened, we would begin to see the very first stars. These population 3 stars have never been seen directly, but in our perfect deep field, they would shine. We'd see them blink into existence, burn with fierce intensity, and then collapse into black holes or explode as giant supernovae. These early stars would light up the cosmic dark ages, revealing a universe that is still mostly empty, but beginning to take shape. Beyond even those first stars lies the edge of visibility. With our ultimate tools, we could see the CMB not just as a uniform glow, but as a detailed landscape, a map of temperature ripples, density variations, and quantum seeds that would grow into the structure we observe today. And maybe, if our instruments are good enough, we could go even deeper, past the microwave background, to see traces of what came before. Maybe even signals from before the Big Bang, if such a thing is possible. With perfect tools, we could also look forward. We could observe not just what galaxies were, but what they are becoming. Over the ages, we'd see star formation slow down. We'd watch galaxies fade, merge, and drift apart as the universe expands. Eventually, we might even see the large-scale structure of the universe begin to empty out, as galaxies move beyond our cosmic horizon, leaving behind a quieter, lonelier sky. And if we go far enough into the future, the light itself will change. Stars will run out of fuel. Black holes will grow, swallow, and eventually evaporate. In the very distant future, only cold remnants will remain. White dwarfs cooling into black lumps, dead planets drifting alone, and perhaps a few exotic particles flickering in the void. Our deep field, which once burst with light and energy, would slowly dim. It would become a record of everything that was, a time capsule of a living cosmos gradually falling asleep. Even in the dark, though, there might be surprises. Some theories suggest that new universes could bubble into existence far away from us. In a deep enough field, with tools that can detect even the smallest changes in spacetime, we might see the beginnings of such events. Tiny distortions, strange flashes, or unexplained patterns. Our ultimate telescope might become the first device to spot another universe being born. Future missions like the Roman Space Telescope and ground-based observatories like the Extremely Large Telescope will go much further than Hubble and Co. But we are still very far from the ultimate deep field, a window not just into space, but into time, physics, and the unknown. The technology of the future's future. If we imagine the far future, not just 100 or 1,000 years from now, but tens of thousands, maybe millions, We enter a world where the tools of science don't just improve, they evolve into something beyond anything we've ever built. A telescope of the future's future wouldn't be just a bigger version of what we already have. It would be something entirely different. A tool that doesn't just look deeper, but changes how we even define seeing. One idea is building telescopes the size of moons, or even larger. A telescope that size would be so powerful that it could spot Earth-like planets around stars on the far side of the galaxy. Of course, building something that massive wouldn't be easy. Even getting parts into space today is a struggle. But in the far future, with technologies we don't yet have, like self-replicating machines, space-based construction, or materials grown from atomic layers, it becomes more likely. An advanced civilization might not build one giant telescope all at once, but let it grow piece by piece. A swarm of satellites could fly in formation, acting as one single lens. Lasers could keep them perfectly aligned, spreading across thousands of kilometers, collecting light together like a single vast eye pointed at the stars. Some scientists have already begun imagining this, calling them aperture arrays. They don't need to be solid mirrors. They just need to act together, synchronized to the smallest fraction of a second. These floating telescopes could stretch across the orbit of a planet, or even form rings around stars. Their view of the universe would be sharp enough to watch a volcano erupt on an alien world, or to read the rings of atoms around distant black holes. But even these are small compared to what might come next. The real leap is when telescopes aren't just large, they become cosmic. A telescope the size of a planet is already huge. A telescope the size of a star is bigger still. But what about one the size of a galaxy? That sounds impossible, but it's an idea worth exploring. A civilization advanced enough to control stars or harvest energy from entire solar systems, something we might call Type 3 on the Kardashev scale, would not be limited by earthbound thinking. They could use the gravity of stars or the orbits of entire solar systems to arrange giant lenses, mirrors, or detectors across light years of space. They might use gravitational lensing to their advantage, but at a completely different scale. Instead of building a telescope to take advantage of the sun's lensing, future civilizations could do the same with many stars, maybe even black holes. If carefully mapped and coordinated, an entire network of these lenses could provide a view of the universe that is nearly perfect, down to its smallest details. Telescopes would no longer be just tools to gather light. They could become instruments that track time, scan quantum fields, or measure the fabric of space with such precision that even the faintest ripples of ancient events, the echoes of a galaxy forming, the flicker of a long-dead civilization, could be recorded and studied. The telescope of Type 3 civilization could be a giant sensor web spread across an entire star cluster, sensitive to all kinds of signals: light, neutrinos, gravitational waves, magnetic fluctuations, and even forms of energy we don't know about yet. Imagine a civilization spreading through the galaxy, not to colonize, but to observe. Every star system becomes part of a larger instrument. Each planet houses part of a detector. Every moon carries mirrors, cameras, or sensors. They might not need to send spaceships anymore. Instead, they see everything from where they are. The whole sky becomes a canvas of living data. And what would they be looking for? Maybe the birth of a new universe, the first flicker of life on a newly formed world, or the last collapse of a dying galaxy. They might use their instruments to test the limits of physics itself, zooming in on the edges of black holes, watching quantum fluctuations ripple across space, or trying to find signs of structure beyond the observable universe. They might not use eyes at all. Their senses could extend into dimensions we can't perceive, like trying to explain color to someone who sees only in black and white. It's even possible that these civilizations already exist, and that we are inside one of their telescopes without even knowing it. If a network of observation tools is large enough and subtle enough, we could pass right through it, like insects flying through a vast machine. Perhaps the universe is already being watched by instruments so powerful and so advanced that they don't disturb anything at all, They only observe. To us, space seems empty. But to them, every atom, every particle, every ray of light is part of the data. We build telescopes one at a time: metal, glass, mirrors, sensors. Each one opens a new window, but the sky remains mostly dark, mostly unknown. Still, we can imagine. We can look ahead, not just years or centuries, but into the deep future. A time when seeing the universe means becoming part of it, when our tools are no longer bound by size, weight, or cost, when observation becomes an act of presence, not just science. When telescopes stretch across the stars, and the entire cosmos becomes the lens through which we search for meaning. What would the back of the Big Bang look like? We are always looking outward. Every telescope on Earth or in orbit points toward the sky, searching for signals that have traveled across time and space to reach us. The farther we look, the further back in time we go, and when we look deep enough, past all the stars and galaxies, we find the CMB. But what's behind that wall? In everyday life, we're used to being able to turn things around, flip them over, look behind and underneath. But in cosmology, the word behind stops making sense. The Big Bang wasn't an explosion that happened in space. It was the beginning of space and time itself. There is no outside. There is no direction to point a telescope and say, let's look behind it. Still, scientists have tried to imagine what the early moments might have looked like. Using mathematics, we can roll the universe back in time, shrinking galaxies, heating up particles, and pushing everything closer together. Eventually, we reach a point where the laws of physics begin to break down, a state of energy and density so extreme that our current theories can't describe it. This is the limit of our vision. But there's also a more radical way to think about this question. Some physicists have asked whether the Big Bang is even the beginning. Maybe it's not a wall, but a bridge. There are theories that suggest the universe didn't start from nothing, but from something else, another state or another phase. In these models, the Big Bang is just a transition point, like ice turning into water. Before the bang, there may have been a contracting universe, a cosmic bounce, or a timeless quantum field fluctuating until something burst into existence. If that's true, then behind the Big Bang becomes a meaningful phrase. Not in the literal sense of turning around and seeing what's there, but in the sense of tracing the cosmic timeline further back. The Big Bang might be the aftershock of something else. Some ideas come from string theory and quantum gravity. In these frameworks, the Big Bang isn't a point of infinite density, but a kind of phase change in the geometry of space. Think of steam turning to water. If the early universe underwent such a transition, then it might be possible to model what came before. One idea is the ekpyrotic model. In this theory, our universe was born from the collision of two higher dimensional membranes in a wider space. The impact created the energy and matter we now observe. In this view, the Big Bang is just the visible side of a much larger story, the aftermath of a cosmic event that took place in dimensions we can't access. Others suggest that time itself may have behaved differently in those early moments. Instead of flowing from past to future in a single direction, time may have been more like a landscape, a place where different directions were possible, but collapsed into one as the universe cooled. In this picture, looking behind the Big Bang is like trying to look at the backside of time itself. These ideas are hard to picture and even harder to test. Even if there is no light from before the CMB, the universe may still hold clues. In the way galaxies cluster, or in the faint signals of quantum fields, there may be whispers of what existed before. What if the universe ends, just out of sight? Space feels like it has no boundary, no edge, no end, but that sense of infinity is only based on what we can see, and what we can see is limited. What if there's nothing beyond? What if just past the cosmic horizon, space doesn't continue forever? What if the universe ends, not in the distant future, but right now, just out of sight? For a long time, Scientists have asked whether the universe is infinite or finite. There are several ways the universe could be finite and still seem infinite to us. One idea is that space curves back on itself. But what if space doesn't loop back? Maybe it just stops, not with a wall or a drop-off, but with a region where there simply is no more space. Just like how a painting has a frame or a video has an edge, maybe the universe only exists out to a certain scale, and then it doesn't. If this is true, it would completely change how we think about everything. For one thing, it would mean the universe is much smaller than we thought. Maybe instead of being one small dot in a vast, endless ocean of galaxies, we're actually near the edge. Or maybe we're right in the middle of the whole thing, but there's still only a limited number of galaxies, a limited number of stars, a limited amount of time and space. It would also mean that some of the biggest assumptions in physics might need to be rethought. A lot of our theories, especially in cosmology, depend on the idea that the universe is the same everywhere. But if the universe ends somewhere out there, then that symmetry breaks. There's a place where space stops. That would make our location special in some way. Not because we're important, but because we're somewhere inside a finite object and not just floating in an endless void. Another thing this raises is the question of why the universe would end at all. What would make it stop? Is there some kind of boundary condition that sets the outer limits? Is there a deeper reality outside of it? A place where other universes exist, or where ours was created from? These questions quickly move from physics to philosophy. They touch on the nature of existence itself. Of course, one reason we tend to imagine the universe as infinite is because it's easier to think that way. It avoids uncomfortable ideas about edges, endings, and limits. Infinity lets things continue forever. It means there's always more to explore, more to learn, more to see. A finite universe, especially one that ends just out of reach, feels a bit like a trick, like a stage that looks vast from the front row, but turns out to be shallow when viewed from behind. What would happen if we ever got close to the edge? We couldn't travel there. That is impossible with current technology. But what if we could observe it somehow? What would it look like? Would it just be darkness? Would space become thinner or behave differently? Would the laws of physics break down? No one knows. And maybe we'll never know. But the fact that the edge could be there, just outside our view, adds a kind of mystery to everything we observe. It also challenges our place in the universe. If we're inside a finite cosmos, then it might mean the universe itself had to be created in a specific way. Maybe it came from something else. Maybe it's part of a larger system. Or maybe it just is, and we'll never understand why. That kind of uncertainty isn't easy to accept, but it's part of science. What we think of as the universe is still just a picture we build from what we can see. That picture is rich and detailed, but it's also incomplete. There could be strange truths just beyond the edge of that frame. And if that's the case, then all of our telescopes, all of our maps, all of our theories are happening inside something that is, at its heart, limited. The idea that the universe might end just beyond what we can see doesn't make it smaller in a practical sense. It's still more than we can ever visit or explore. But it adds weight to the question of how we fit into the whole thing. It makes the mystery more immediate. It makes the silence of deep space feel a little more personal, because maybe, just maybe, there's a line out there where everything stops. And we're on the inside, trying to make sense of it all. What sort of exciting future discoveries on this topic are you looking forward to? Comment down below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.